should be a platform, a complete platform, a framework for developers to test, to experiment the X-apps under a specific network condition. What we propose is X-Start. Okay? This is the architecture of X-Start. X-Start enables the developers to integrate their X-app in a simulation environment under real network condition. At the lower layer of the architecture, we have NS3 simulator. In particular, we leverage NS-ORAN. That is a specific version of NS3 that simulates the RAN environment. The simulator is linked via A2 interfaces to the near real time, that is in the middle. We leverage call-ORAN RIC, that is a near real time RIC, that provide two specific things. One is that provide data from the RAN to the X-apps via the shared data layer, and may act as a broker if you have different X-apps. At the application level, we have the X-apps. All of them are deployed in a Docker container, so it's very easy to a developer to take X-Start and start to test and implement their X-apps. A first version is available in our repository, that is Unibo. But I want to say one thing about the Grand Challenge 19. Me and Professor Bianchi, Professor Giacomo Verticale and Professor Luca Foschini start to disseminating the open source and open data things. I know that this is not the right place, but not the right time. But we will disseminating this information, more information about the open source challenges. The idea is to have all of the projects that are open source in a repo or in a library that is restart. Okay, this is the main things. Okay, that's my conclusion.
Thank you. The second one is Eugenio Moro.
Thank you. Good morning. So in this quick pitch, I'll talk about this line of research. Now we gave it this title, Programmable and Open Network Intelligence for Connected and Autonomous Vehicles. For me, it's the first time that I work with vehicular communication. But my colleague Francesco contributed the most to this research. Research is an expert on vehicular communication. What we try to do during the end of our PhD is putting together the two things that we work on, vehicular communication and network programmability. So starting with network programmability, we are considering ORAN, which I feel I said what it is a million times, but here I go again. It's technically an architectural overhaul of traditional radio access network. We have just 5 minutes. What's important for us is the yellow brick in the middle, NRT-RIC, or RAN Intelligent Controller, or RIC. This is a softwareized control loop. It's entirely standard. It's entirely software that through some open interfaces exposes some APIs, control knobs and telemetry primitives from the hardware. And these APIs are exposed to X-apps where you write your solution, whatever it is, to control the network. What's cool about this is that you do this independently of what kind of hardware you have. And we said, you know, a lot of issues that we have in vehicular communication in V2X, we could solve them with this kind of architecture, but nobody did it, surprisingly, so we tried. And these are the few challenges that we said that could be easily solved with the ORAN approach. And we had this perspective of a full stack programmability for vehicular networks that in this case entails beam management, resource allocation for direct communication between vehicles, vehicular connectivity, and then digital twin. And these are ordered in some kind of stack fashion. The first thing that we did, step 0, I would call it, is to integrate them. Because ORAN wasn't supposed to work for vehicular networks, but you will see it works very well for vehicular networks. It just misses some kind of integration. I have no time to show you that, but we could discuss it offline. I'm sure we won't. But beam management, we designed an XUP that does beam management. As you can see here, we increase a lot the spectral efficiency, and crucially, we decrease the training time. We compare these, our XUP, it's implemented in simulation, it's a full XUP, with the standard, because XUPs are, well, if we had here in Catania or a network, we could deploy an XUP, this kind of XUP right now, and it would already work. So there are state-of-the-art solutions that work better than our XUP, but they are not applicable to a real-life network. Then resource allocation, we said, let's try to solve the direct vehicular communication resource allocation. So we compared it to standard mode 2, which is the standard way of allocating resources between vehicles. It's decentralized, and we compare it with an XUP, and it works much better. We have no collisions, which we have a lot in mode 2, and a lot of throughput. Then, vehicular connectivity. Why is it important? Vehicles communicate with each other. Sometimes there's a blockage, and we need to select a new path. So this is not easily done with the standard. There's a lot of state-of-the-art, but it's not easily done. An XUP that you deploy on your network, if you're an operator and you're giving V2X services, can basically monitor the condition of the network and select other vehicles to communicate, to establish a new path for two vehicles that cannot communicate anymore. This is extremely important. And last but not least, we said ORAN is capable of maintaining, creating, and exploiting a digital twin, and this application is for the selection of roadside unit. So we use the digital twin, well, it's a simulated digital twin, but we implemented it, we integrated it with an XUP, and we show the use case of using that for vehicular selection. Last slide, I don't know if I have enough time, but this is an award that is given out for impact, so we talk a little bit about impact, and we started working on this 1 year ago. So this is what we could do in 1 year. We have 2 conferences, 1 journal, and 1 magazine. Not all of them are accepted, unfortunately, not yet, I hope. Then collaboration with University, Polytechnic di Torino. We are integrating in their MS Manet their simulation, our ideas. Unicasino, with which we are collaborating for a paper, and FUB. Then regarding Restart, our architecture has been selected as a POC, one of 4 or 5 POC that will be completed during 6G YNET. Then we presented this work in Bologna and Bari. And we presented this work at an ORAN workshop. Talking about impact, I think this is one of the biggest impact points, because we went to ORAN to present that. And then it's done. We have some industry collaboration with Leonardo and Airways on this matter, and we could present this idea to some people from other universities, and they were very interested, and I'm done. Thank you.
Thank you, Eugenio. Thanks. Next is Daniele Pugliese.
Thank you. It's a pleasure to be here. I'm Daniele Pugliese from Polytechnic University of Bari. And today I'm here to briefly introduce our recent work written in collaboration with some colleagues from University of Rome, Tor Vergata, and Rome Application Research System. From the title, Integrating Terrestrial and Non-Terrestrial Network via IAB Technology, System Level Design and Evaluation. Well, we all know that the third generation partnership project has an interest in integrating the actual next generation radio access network with the so-called non-terrestrial network. And this is evident from the recent reports and specification. So in our work, we considered the possibility of adopt integrated access and backhaul, which is basically a technology that allows us to reuse the same radio resources of the radio access network, 5G radio access network, to backhaul data backhaul data to another node and then to the core network. So we consider the IAB technology to integrate low Earth orbit and geostationary Earth orbit satellites in our network. So for the sake of time and space, I just introduced you the main 3 contributions of our work. And as the first point, we started by analyzing what is the theoretical background of next generation radio access network, non-terrestrial networks, and integrated access and backhaul. And then we analyzed what are the main issues, the main adaptations that are needed to make this integration works. Because if we have satellites in our architectures, we have higher propagation delay, and so we have to extend some timer, we have to resize some transmitting and receiving window. Then we also propose basically two topologies, two scenarios that are tailored to support 2 services. The first one is basically a sensor network, so IoT-like traffic supported by a low Earth orbit satellite that works as an EAB node. And the second scenario that we propose and then analyze is to support broadband services, so multimedia streaming and so on, thanks to geostationary satellites that works as an EAB donor. As a second point, we analyze in detail the design and implementation of a tool that basically simulate end-to-end EAB architectures. And in particular, we implemented the EAB node that basically receive data from the access from user equipment and relay them to another EAB donor, another EAB node or the EAB donor, and also vice versa. So we implemented this node in the simulator. We also modeled the, let's say, Earth to space link. And so we needed a mobility model for the satellites and to model the, let's say, the channel and what is the block error rate. What are the block error rate curves for each modulation encoding scheme. And in the end, we adopted this simulator to conduct a simulation campaign with which we analyzed these 2 scenarios in terms of registration time, so how much time a user equipment in the access, how much time is needed to register to the core network, what is the link capacity of the access and the backhaul link, and moreover also the delays for the single hop and also end-to-end. And in the end of our work, we derived some consideration about the applicability and what are the limitations of integrated satellites thanks to EAB technology. That's all. Thank you.
Via venendo younger certo io.
Very young, very young. So, okay. So this is an idea that came to us by looking at what is the metasurface and revisiting, what is the state of the art. So, and this is going to the framework where, we want to make a waveform processing. So, so the concept is illustrated here. So, ST space-time coded modulation, is the one that you see on the left-hand side. And, it's essentially the following. So if you have a metasurface and you modulate, with a periodic signal, what's happening is that you generate a set of harmonic of the backscatter wave. So that backscatter wave, is the same, following the same Snell law or, generalized the Snell law, which is, bending the ray in the direction according to the gradient in space. Okay, so this was the state of the art. So, what we propose is the following. So instead of, injecting, modulate, in a temporal part, instead of modulating with a periodic signal, we can modulate with the data stream. So the idea is that we inject the data stream in what is called data. How can I use this? Is over there?
Yes.
Oh, how can I, here. Okay. This data stream over there. Okay. And so that means that if I have a data impinging and a data stream that is modulating in time the metasurface, then the backscatter is the data stream A and the data stream B. So that means that I'm making a superposition of two streams, and now the data A can be without data in the sense that there's just a plain wave impinging, and then I have a data B, or I can make data A and data B that are backscattered directly. And in this way, we make what is called, the full duplex. So this idea is that we can make a full duplex by a backscattering modulation. So there is some theory behind, but the story is that with the metasurface, we impose a spatial gradient, and here we impose a spatial gradient and a temporal gradient. So imposing that, we get the space-time modulation that is illustrated here. So how can we use that? Well, the idea is that to use it, to put as in devices where the power is very low, and we can operate as a backscatter modulation essentially. So we put, you have a MU, which is illustrated there, and then we have a space-time modulation there that is, transmitting the data backward, okay? As you remember, is operating in a reflection mode. So if we look at the bit on the theory, well, there is a certain region between the incident wave, the reflected wave, and, the bandwidth that define a certain region, which is illustrated there, where the waves are not propagating but are absorbing, which is the evanescent wave. So, there is a study on how to make this because it's not always straightforward. And if we look at, the entire, and on the right-hand side, we have the spatial modulation as any metasurface, and we have a temporal modulation we need to superimpose. Now, since the temporal modulation implies that I need to use the devices that they need to have a certain bandwidth, so what we have been thinking, we have been thinking to aggregate the temporal metasurface, the temporal modulation in a cluster, so in a set of, group of atoms that are modulated in time. So this is on the right-hand side. So, and out of that, what you can do, you can evaluate how much uplink bandwidth you can get, we can get, and the spectral efficiency, which is the plot on the left, versus K. K is the number of clusters we can use. So K equal 1 is the minimum cost. And this is compared with the perfect compensation, which is the one that, this line here. So it means that, we can get in the order of 2-4 clusters. So it means the metasurface can be divided in two parts to make the time modulation. And on the right-hand side, there is some comparison on the signal-to-noise ratio versus, the spectral efficiency versus the signal-to-noise ratio, compared with some compensation that we are proposing. Everything is in this paper that was published in JSAC on June. Thank you.
Perfectly on time. This is the experience. Last but not least, Francesco.
Good morning, I'm Francesco Mancini, and today in this speech I will present our work about security assurance testing in 5G core networks. Security assurance tests verifies that a component correctly implements a security feature. We may think that this involves two components, a system under test and a tester that send a set of messages and evaluates the reaction of the component under test. However, in 5G core networks, we have a totally different scenario. First of all, we have that a network function under test communicates with multiple components simultaneously. The tester has to manage all these components during testing. And so the tester has to coordinate all these components and also trigger anomalous behaviors in order to verify corner case scenario of the security specification. To make the things works, the communication involves multiple protocols and that the tester has to take into account. There are several commercial solutions about security assurance testing, and they share a common approach. They take the network function to test and surround it with multiple simulated network functions. In this case, we have full control and full customization of test infrastructure. Of course, we have total control of an emulated network. But however, we cannot perform tests directly in the operator's network. And this is a labor-intensive approach and usually is performed only on the first release of the network function. We propose a totally different approach. We take the whole network and embed it with a set of proxies that intercept the communication and allow runtime modification of the messages in order to trigger the anomalous behavior in the network. This infrastructure is managed by a centralized controller that handles the coordination, and it offers an API to allow testers to write their own test. This API is based on state-of-the-art frameworks used by industries for perform software testing. Of course, this is called SCSDK, a development kit that allows testers to write, deploy, and execute their own test. Of course, we guarantee the same advantages of the previous approach, and in addition, we can perform this test on premises directly on the network operator, on the operator networks. We can integrate our infrastructure in DevSecOps tools, and we can perform the test at runtime on demand when we need. This is the whole timeline of development of SCSDK. Started at the beginning of 2023. We evaluated our framework with open source solution, and we can state that there is a poor security posture. We may think that these open source core networks are only used for research purposes. However, there are several commercial solutions, especially for 5G private network, that relies on this open source implementation. We presented our work to ACN, namely the Italian Agency for Cybersecurity, and they show interest to our works. In fact, one of their missions is to evaluate the security of critical infrastructure, and the 5G is one of them. And our work, our project can be used for a potential framework for supporting this test. This is the current version of SCSDK. We are continuously developing it towards to be integrated in more realistic networks. And we suppose that it will be based on containerization and deployment with Kubernetes orchestrators. Thank you for your attention.
Thank you. So now the Commission has all the information for taking a decision that we will announce at the end of the day. Now we continue with the regular program, and the first part will be sharing. Giacomo Morabido will be sharing.
Okay, so the first talk will be by Carla Chiasserini. Okay.
Okay.
Please.
So yeah, thanks. Yeah, I will be brief actually, because I would like just to give a high-level idea of what the super project, that is the acronym for Sustainable Edge for a Highly Demanding Hyper-Distributed Service, is doing. But actually, I would like to talk in particular about our recent contribution that has been translated into a position paper that presents our vision of programmable networks and for the support of distributed services. So this talk would not be on a detailed solution or a technical scientific solution among, of course, those that have been developed within the work packages of the project. Rather, it will aim at presenting indeed this, let's say, long-term vision that is the result of brainstorming among all the partners contributing to Super. And well, we actually would like to thank Nicola and Antonio, because they asked us initially to think about a vision. So what would be, according to our sensibility and knowledge, the kind of revolutionary concept in programming networking? And at the beginning, of course, we didn't take it very well. So we said, well, now we have to write this position paper and so on. What can we do? But then actually it worked very, very well. And also it helped us to brainstorm all together, academic as well as industrial partner, in order to envision the future, of course, according to, as I was saying, our own sensibility about programmable networks. Just to recall very, very briefly what the Super project is about. So programmable networks aimed at providing quality of service, quality of experience, also for those services and applications that will support virtual interactions and interaction with humans, services that need to be distributed and act in real time. So challenges that are posed by services that are exemplified here. And in particular, we aim at, as I was saying, fulfilling the user needs, so quality of service and quality of experience, but also to have reliable networks and sustainable networks. This is through reconfigurability, which should be quickly and efficient, and indeed to be reconfigurable is the main property that we actually leveraged to develop our vision, as we will see in a minute. But about sustainability, I just want to recall that the project aims not just at energy efficiency, but also the reuse of hardware, and so is like a more, let's say, comprehensive also vision of sustainability. That said, there are, of course, several work packages within the project that are working towards the achievement of these goals, of these objectives, through the development of a software edge mobile platform that needs to be reconfigurable, as we were saying, so highly dynamic. And of course, we are using also AI and ML, and actually Sergio already presented yesterday, Sergio Barbarossa, for example, a contribution by Polito, leveraging AI ML in order to make the edge intelligent. But what we would like to present now is indeed this overarching innovation that we have conceived as a consortium of the Super project. So the project addresses different tiers of the network, including the radio access network, of course, the edge and the core. All tiers are considered as programmable. And based on that, we developed this concept that we called morphable programmable networks, MPN. So what is that? Well, we started by observing that in the literature, focusing on programmable networks, we have the concept of vertical programmability. That means that given a node protocol stack, we have, of course, the possibility to dynamically program the different layers of the stack. And we have a horizontal programmability that is instead given a protocol layer, we can indeed act on it and make it dynamic and programmable across different domains and across different network tiers. But what was missing is actually full programmability that we exemplified here in this image, considering both the possibility to program and configure dynamically the protocol stack within a single node as well as across different nodes. So to further clarify the idea, well, let's start from, let's say, why we need this full programmability. Of course, in order to support different applications and services that are more and more challenging, and of course, there are emerging services that aim at realizing immersive and cognitive applications with interactions with humans, with interactions with other devices, heterogeneous, highly heterogeneous devices. Well, we need networks that indeed have to adapt very, very quickly to the user, to the application, to the service to be supported, to the environment, the context where they are operating. So we know that, of course, network slicing is one technology that is very important and that is functional to that. We have scenarios, application scenarios that are extremely relevant where indeed this reconfigurability is needed. And this is also supported by actually the activity within 3GPP. We have mentioned here one of the working groups. Our industrial partners indeed, let's say, double-checked and helped us to also address these needs that are emerging within 3GPP through this vision. So, of course, the importance of native AI and the coordination between network and computing. But also in terms of network security, being highly reconfigurable means that we can confound the attackers and introduce more and more, indeed, randomness and unpredictability. So our morphable networks essentially aim at implementing a management plane that should operate on a longer time scale and define the dynamics of the system, of the network system, and allow the system to adapt, as we were saying, to the environment and to the context, and then control and data planes that, of course, need to be fully programmable as well, and that are going to act on a shorter time scale, essentially addressing more real-time requests. So this is the reference architecture that we developed, where we have within each node, of course, the different protocol layers, and an entity that is the management on the management plane, that is the morphable engine, and that is responsible for monitoring coordinated programmability across the nodes, but also local node programmability, And this morphing engine will act according to policies that are established by the domain morphing engine entity that instead is responsible for maintaining the service catalog and essentially what we called protocol stack blueprints. So the idea is indeed that within a single node at the different layers, we can have different functions that can be enabled. For example, in terms of routing a layer 3 or medium access control schemes at layer 2, and each of them can be implemented. This is just, of course, an option as a container within a container that will be activated or not depending on the protocol stack blueprint that is going to be enabled within that node. And of course, through the domain management entity, we are going to coordinate across the nodes of the same domain. That is essentially fundamental in order to let the nodes that need to interact being able to, of course, communicate. Within each node, then we have the morphable entity, again, on the management plane that applies the blueprints within the protocol stack of the single node. So challenged actually by the reviewers of the paper that we wrote, that is for which we received a major revision, is now under a second review round. They asked us, of course, how are you going to implement these morphable programmable networks and in practice? So we brainstormed about it, and essentially we found that a viable solution could be to extend what has been conceived within ORAN for the radio access network to the different protocol stack, and so to consider the whole protocol architecture of our nodes and our networks. But essentially the DME, so the domain management entity of our morphable networks, could be designed akin to the non-real-time RIC, while instead the ME will be akin to the near real-time RIC. So this was essentially a kind of solution that we envisioned and that actually we are going to aim at in the future. Of course, there are many research challenges because in order to realize these fully, let's say, portable networks that can be conceived also as a given set of devices that can reconfigure quickly, dynamically, depending on the context, depending on what they have to do, depending on what they have indeed to interact with. We need to design this fully programmable data and control plane. So there are clearly challenges in doing that. We are going to exploit AI ML, but decision making on different time scales and considering also, let's say, geographically or space related issues is a challenge. And then the heterogeneity of the devices that, of course, have to be involved. And finally, security and privacy threats are there related to the decision-making process based on ML, but in general being these networks that should adapt to the environment, to the context as much as possible. They are going, let's say, to absorb whatever the environment offers, and therefore they might be more exposed on one hand to attacks. On the other hand, as we were saying, the ability to reconfigure themselves continuously will help counteracting attackers. Now, just to conclude, just a final observation, this is our future vision about programmable networks. Of course, within the project, we are developing more, let's say, detailed scientific and technical contributions, and in particular, the design of an orchestrator also as an input to the Grand Challenge 10. I don't want to go into the details, of course, of the orchestrator scheme that we have been working on, but just to say that our intention would be to, let's say, try and merge these activities within Super, that are this far-fetching vision of programmable networks on one side, and the activity that we started since the beginning, of course, based on the description of work of our project, about the orchestration of the network. And so the intention is that actually to our activities related in particular to network and service orchestration towards what is the vision of morphable programming networks. And this is essentially our challenge in the rest of the project duration. So I would like to thank all the partners of the project who have actively contributed to developing this vision. And so hopefully we'll have this position paper out soon. And I must say that that will be a great achievement for us, because we have all together worked towards this. And thank you all for your attention.
Thank you very much, Carla. You have been very good. So the next talk will be by Sebastiano Milano, who is already here.
Okay, so I will start, I think, with let's say, continuing what Carla just discussed, focusing on the programmability aspect of these next generation networks, with a focus on the Super and the Leggero project, but mainly on the data plane, let's say, programmability. Let me start by giving you, of course, we have seen during the presentations yesterday that the networks are now basically programmable at every layer. These key innovations have been driven by SDN, network function virtualization, automation and orchestration, the integration of AI and machine learning. Because these innovations allow to increase the level of programmability of the modern networks. Now, there are different levels of programmability that we have today. We start from the data plane programmability that allow us to, let's say, transform what we had traditionally, in the traditional switches that were able just to be programmed, not be programmed, but let's say configured to perform specific real-time packet processing. Now, with the introduction of specific ASICs or FPGA, we can modify the behavior of the networking switches by using some high-level languages like P4 to modify the behavior of how these switches should process the packets, implement custom protocols or forward these packets. Then we have another level of programmability, which is the control plane programmability, that allow us to specify how we can forward packets or how the different policy, the switches should forward packets across the others. And then there is another level, which is the service layer programmability or service level programmability, where we have different cloud computing, edge computing, fog computing. They use different orchestrator platforms like Kubernetes, OpenStack. They allow us to run network functions, network applications inside containers, VM. We have now this other level of programmability where we can put different applications in the cloud, and then we can orchestrate this application across the network. Now, if we look at the vision of all these layers of programmability, we can see that vertically we have all these layers together. But what is important that in the past or during the years, all the researchers, even me, we have worked only on a specific layer. No? For instance, I started working on the data plane level of programmability. Other people are working on service placement, orchestration, all this stuff. They work on another level of programmability. But we don't see a common way to, let's say, exploit or use all this level of programmability. So the network is programmable, every layer is programmable. How can we really exploit this programmability in an efficient way? And this is exactly the idea that we have in the Leggero, as Carla also said, Leggero and Super project. We have two main fundamental introductions. First of all is how to orchestrate all these different layers of programmability, and even more important, how to do it at runtime. No, this is the real introduction. So I will just go briefly by presenting the vision, which is basically what Carla presented, the challenges and some of the solutions that we are deploying, developing at Polyme in our group to achieve this vision. So I will try to be more practical by showing what we are really doing to achieve this level of programmability. So the first concept is the full programmability. We have seen all these layers, and we need to find an abstract way or a transparent way to exploit all these layers in an efficient way. Now, we can see this programmability from the vertical point of view, where we have all this layer of the networking stack that should be used, but also across the network. If we have different parts of the network, the core edge of the network, we should split the application in a way that can rely on the programmabilities of these layers. Of course, there are different challenges to achieve this. First of all, every layer is programmable, but every layer can be programmed in a different way than the other layers. We have different languages, different frameworks, different tools that are used for every layer of programmability. How can we manage this complexity, all these programmability layers in a transparent way? We need to find some abstractions that allow us to find a trade-off between let's say, simplifying the writing of new application, but without losing too much insights on what the programmability allows us to do. The second challenge is, of course, these layers can be programmed again, but for instance, for the data plane point of view, they can be hardware devices that are developed by different vendors. They have different standards, they have different protocols, they have different ways to be programmed. How can we manage this level of programmability in a way that they can work seamlessly together? The other important concept is, again, the morphable networking. So, again, all these layers of programmability, how can we dynamically reconfigure every layer so that it can be efficient at runtime with the actual configuration or with the actual traffic that is receiving? If we look at the figure here, now we have different data plane programs. We have the switch.os and the P4 data plane that allow us to program the hardware switch. But at the same time, we have also the host, which is basically the end host, the server, where we run our functionality, that has a NIC. These are the data plane part. But then we have the controller. So the idea is we specify an high-level intent. So we specify what the network should do, and then there will be a compiler or something that will decide how to split this program across the different layers. But the important part is the introduction of this fine-grained telemetry, which is basically the component that should gather runtime information about what the application is doing or how the network is behaving, put all this information back into this runtime optimization layer and create a closed loop so that the network can continuously re-optimize itself. Now, of course, there are challenges to do it. Basically, balancing the flexibility between performance and efficiency. What are we doing in Polyme to achieve this vision? So let's see two different examples. The first example to show you the integration of the different layers of programmability, And the second example is how to do it at runtime, how to re-optimize the applications at runtime. So the first case that I want to start with is a single stateful network application that is running on a specific server. Now, as you can see in this figure, there is a network function and then there is a server. This is a software network function that is executed in a data center of an hyperscaler or a telecom operator. If we look at a bit inside of what is inside this server, we can say that there are different cores where the network function can be executed, and then there is a NIC where packets are received and then sent to the different cores. Traditional ways to achieve, let's say, the most efficient way of the execution of this network function, unfortunately, requires the network function to access some shared data structures. And of course, when there is a high memory contention on the access of this shared data structure, we need to use locks, we need to use mechanisms in order to guarantee that the access to this shared data structure is coherent. And as you can see, incrementing the number of cores doesn't really increase the performance of the application. But if we look at how this end host, from the vertical point of view, this end host is actually composed in next generation networks, we can say now we have P4 switches, so programmable switches, but we also have programmable NICs. Programmable NICs are, they have like FPGA, so they can be programmed, and we can potentially offload some of the functionality from the end host into the NIC. So we can help the parallelization of the network function by offloading some functionality to the NIC. Now, the NIC is the entry point, the NIC or the programmable switch. The NIC is the entry point for all the packets. Is it possible to offload some of this functionality directly into the NIC so that we can parallelize the application and avoid the cost of accessing the shared data structure? So I will not go too much into the details or the technical details of this, but the idea is that, of course, by exploiting this vertical programmability and the different layers of programmability of the networking stack, we can offload some functionality into the NIC or the switch, and we can achieve parallelization where every packet can be processed by every instantiation of the network function on every core without having to access a shared data structure. If you look at this figure, compared to the previous example, the traditional way, which is the green and the orange figure, the blue line allows us to achieve and scale linearly the throughput by incrementing the number of hosts, the number of cores. So this is, in my opinion, I was going to say a perfect example. Of course, it's my work, so I cannot say. It's a good example, let's say. It's a good example of an application that is relying on all these different layers of programmability, these different aspects of programmability that we have in modern networks to achieve better performance, as you can see in the blue line. Now let's move to the other aspect. So we have seen how to exploit, at least what we are doing in Polyme. Of course, there are different works that we are doing as part of Leggero and Super, but at least for Polyme, we have the vision. So what are we doing to achieve this vision? The first work for the full programmability. What are we doing for the runtime programmability? How can we at runtime modify the application so that it can exploit the runtime information and then modify itself in a way that is more efficient? This is something that I discussed yesterday in the 5-minute pitch, but many of you were not here, so I will 3 minutes. In 3 minutes, yes. I have 3 slides, so 1 minute per slide. So we have the software data plane, which is our application, and then originally, traditionally, the ways to compile this application is that we use we take the source code of the application, we use a standard compiler, and then we create a network function data path, which is completely agnostic to the actual configuration. The idea that we had is, okay, but there are also runtime information that we can exploit. What if we take the runtime behavior of the network function and we put it back to the compiler, and at the same time we do it also for the workload information. So if the network function will be compiled with the knowledge of the runtime configuration and the runtime traffic that the application is receiving, maybe we can apply smarter optimizations to the source code of the application and create a network function customized data path at runtime. This is what we did. The compiler that we created is called Morpheus, just to remember the idea of morphable networking. And this is, let's say, at high level how Morpheus works. So there is an analysis step that allows us to basically understand at high level what the application is doing. The compiler should work for every type of application. So we don't know anything about the application that is going as input to the compiler. So we analyze the application. We then perform some instrumentation. So we add some instructions to gather runtime data, the application, and then we apply some optimization. Now, these optimizations are compiler-specific optimization, like dead code elimination, data structure specialization. We can re-optimize the cache usage into the application, and then achieve better performance. This is exactly what we did. We applied Morpheus to real-world applications. Like, for instance, Catran is a load balancer used by Facebook. Meta in production, we managed to achieve from 5% to 97% improvement over Catran. For this reason, also, Meta gave us a donation for the work that we did. And yeah, basically, this is the idea. So now we have, at least for the data planning part, we have full programmability, so we can exploit the different programmability layers. And we also introduced the concept of runtime programmability by reapplying the optimization according to the runtime traffic. I will go super quick if I have another minute. Of course, this idea of runtime networking, runtime programmable networks introduces some future directions and some future challenges. So it's a completely new, at least in my opinion, is a new area that we should all study and investigate. It brings new challenges to the networking field. Of course, I cannot live without putting the AI word in a presentation. Of course, we can rely on AI. For instance, for the optimization part, we can recompile the application and apply some optimization where the machine learning model is able to understand automatically what are the optimization that we can apply. Right now, in the compiler, the optimization are fixed. They can exploit my domain-specific knowledge of the field, but maybe a machine learning model can be trained not to do it automatically. Runtime networks also bring new security threats, that we should, we have this network that will decide automatically how to re-optimize itself. An attacker can exploit, these runtime optimizations and maybe introduce new security threats. And we need to define interoperability standards. We have all these layers. How can we program them across different vendors in a standard way? And finally, we need to find new algorithms, study new data structures, and way to optimize and scale the performance of the applications. The networking speed is increasing considerably. CPUs are not able to cope with this speed, so we need to use all the layers, including the hardware, to reach the speeds that we need today. Thank you for listening.
Thank you, Sebastiano.
The next speaker will be Andrea Pastrella.
Good morning, everyone. Today I'm wearing actually two hats. My proper restart hats, I will wear it this afternoon. This morning I'm wearing this other hat and present you what we're doing in this initiative, which is called Slices. which is an S3 research infrastructure that has entered the S3 roadmap in Europe a couple of years ago. In this initiative, we are aiming at building a pan-European research infrastructure for our community, actually, together with others. So, in the interest of time, I will skip a few details in the slides. So you might be well aware of the concept of research infrastructures in Europe, but maybe you are not. So allow me to spend just 1 minute to give you the framework. So in the European Commission, there is a specific part of the program which is called S3, which supports research infrastructures. And a research infrastructure is considered to be a scientific instrument to support scientific communities. So it's not so much oriented towards industrial community, towards industrial innovation. It's a way to support experimentally driven research in different scientific communities. And there are very big examples of these initiatives. In our community, as a matter of fact, this is not so wide spread as a concept. And there is an additional point that if you look at typical research infrastructures, of course, this one that I put in the slide is the most famous, the CERN infrastructure. So every research infrastructure has an ICT component, a strong one. So if you consider CERN, there is a lot of ICT there, of course. But the research community that CERN is addressed is not ICT. It's, of course, the community of physicists. And there are other examples in the areas of other scientific disciplines like medicine, earth sciences, and so on and so forth. But the common theme is that if you are a researcher in that area, you have a reference infrastructure, a big one that is sustainable, that stays there for decades, where you go, where you run your experiments, and because you run your experiments there, your results are replicable and are more trusted by the community because that infrastructure is a trusted instrument. So in our area, in the ICT domain, actually, we don't have this yet. And of course, I mean, we don't aim to be the CERN of ICT, of course, but the model is that one. So Slices is the first S3 infrastructure that has been put in the S3 roadmap in order to support our community as scientists and not to support ICT components of other research infrastructures. So this is a big difference. And this, by the way, is also the reason why I'm talking about this topic in this session, because what Carla and Sebastiano has presented before are perfect examples of tools that we try to use in building the infrastructure, but for which you could also use the infrastructure as a scientist to test their performance. We are not alone in the world doing this exercise. There are other initiatives around that are quite similar and with whom we are peering. Probably the one that you know best is the one that our colleague Tommaso Melodia is building, has been built in the US since many years, and as a matter of fact, power is one of the infrastructures we collaborate a lot. And if you have the pleasure to attend, for example, the Lipari School next week, which is organized by Slices this year under the chairing of Professor Palazzo, Tommaso will be, and his team will be giving several talks because we are building joint initiatives with them as well in the framework of Slices, and there are other similar initiatives in other parts of the world. So Slices has been started a long time ago. I mean, if you want to enter S3, it's a long journey. It took a lot of time and effort. It started back in 2017, and now we are in the roadmap, and this is the set of countries in Europe that joined forces for building this initiative. I, of course, will not go into the details. There is a lot of partners in each and every of the member states. As you can see, primarily it is an academic endeavor. Of course, we have strong links and support from industries, but again, this is supposed to be because ESFRI is designed like that to support primarily scientific research more than innovation. And the ESFRI life cycle is well structured, very well structured, long and complex. Right now, we are in the preparation phase, which means that we are not in operation yet. In the preparation phase, essentially, you build all the legal governance framework, you get involved all the member states, because it is the member states that fund those initiatives. And we are refining and finalizing also the technical design. So just to give you, again, a bit of context in the timeline, this is a long-lasting effort. You have to have this time of ambition, this kind of ambition in order to be in ESFRI. So as you can see, the plan is to be operational at least until 2040. And right now we are in the preparation phase. We are starting beginning next year. Actually, we are anticipating it a little bit. We are going to be in pre-operation starting this fall. In pre-operation, it means that we open very few selected services for testing with real users, but also as a sort of a debug of the services that we are going to be offering in operation. But full operation will start beginning 2026. And the complete operation will be from 2029 until 2040. So it's a very long time effort, but which gives also sustainability, a sustainability framework. In the meantime, we are designing and building the infrastructure through dedicated European projects. There is a family of projects. I will not go into the detail. There are a couple of them, sorry, this slide is a little bit old, that are already going on. These two in particular, where there is a significant participation also of the groups, both from CNR and CNIT, that are involved in this initiative, and I will talk a little bit about them later on. And again, we are cooperating with several other countries outside of Europe with similar initiative. Right yesterday, we have got notice of a new project which is a small one, but for bridging out to Africa in order to, help the African ecosystem to develop their skills in this area in order to build similar services also in developing countries. I will go very, very quick. As I said here, in terms of technical aspects, the way we operate in slices is essentially the following one. From a technical standpoint, we define blueprints. So blueprints are the thing that we try to do is not to say we have test beds which are generic and we want to integrate, federate them. This has been done already a lot in the European Commission in the past 2 decades. The idea we try to explore is a little bit different. So we identify research communities, big research communities, like, for example, the community working on post-5G network, but there are other examples. So we talk to those communities, which is also the way why we are talking in this framework, and the next week will be another opportunity to do that. We identify which are the main topics, the main priorities that those communities would like to have to work on, and for which slices could help. And after that, we go and we develop a so-called technical blueprint, which is the way in which we can implement those functionalities that our colleagues would like to see and use in our testbeds. So it's not starting from the testbeds themselves. I have a lot of compute machine, I have a lot of networks, and I want to, make them available. But it's the other way around. What the communities would like to see in those testbeds. And in the case of the 5G blueprint, as we call it, actually we call it post-5G blueprint. Essentially, I will not spend a lot of time because it is essentially aligned with the architecture that Carla and Sebastiano were presenting, not the morphic one, let's say, but the most standard one, of course. And this is the challenge there, because we want to be future-proof, so we want to be ready for the next technical innovation, but we need to build a working system. So this is, as you understand, it's not simple. So it's just one last bit. It's a European infrastructure, so it's distributed. We have a central control. And in the case of post-5G, of course, you can disaggregate your function. You can only implement the run, only implement the core, exploit the core that is developed by someone else, either in Italy or abroad. So essentially, you pick in the blueprint the part that is more interesting for you, you implement it, and the rest is provided by the rest of the infrastructure. And if you are an experimenter, you have many ways of using it either as a black box, or you can go into the detail and modify the parts of the architecture that you want to test. How we are organized in Italy. So in Italy, we are mixing up the fundings that we are getting. As I said, S3 per se doesn't provide you a lot of funding, but it gives you a sort of a label through which you negotiate with the member states for funding, and we are in the process of negotiating this with our ministries in these days. But in the meantime, we are using the project as the one that I mentioned before, that we acquire as a consortium in order to sustain it. And we are organized. This is the current map of the partners. We organized ourselves according to three partnership models: CNR, which is leading, CNIT, and CINI. And thanks to this organization, we are very open to involve anyone who is interested without changing the partnership, which is a good governance model. And this is the current map of what we provide. But again, this is very open. And as you can see, CNIT is very well represented through the Genova lab, the Catania lab, and the Palermo lab. And Raffaele Bolla is the head of the CNIT effort in this initiative. Again, we are expanding. 5G has been the first blueprint. We are building also a cloud-to-edge and IoT blueprint, which is coordinated at the overall infrastructure level, at the European level, by University of Bologna, by Professor Paolo Bellavista. Quantum computing is in the landscape. We are discussing about having a blueprint also on integrated sensing and communication. So, and we are there to stay. I mean, the efficiency of that is that it gives you a sustainability framework. So what are the advantages? If you are an experimenter, of course we are not operational yet, but once this will be operational, and if we achieve our objectives, if you are an experimenter, instead of doing your experiment in your lab, which is fine, but your lab, you know it very well, other people might not know at all it. If you do the same experiment in an instrument like that, the ambition of ours, and this is the S3 model, is that your experiment, your results acquire additional trustworthiness because they are replicable and they are built in an open environment that anyone knows. If you want to integrate your test beds, and this is what we are doing, by the way, all the groups that I mentioned are doing that pulling together the resources that we are leveraging from Restart, but also other projects. Of course, those resources serve the needs of those projects. So what we are doing in Restart primarily serves the Restart purposes, but as a sustainability measure, everything that we are doing there will be eventually translated into under the Slices umbrella. So if you are an experimenter, of course, there is no free lunch. Being in Slices is demanding. You need effort, as our partners can tell you, but the advantages is exactly that one, that you are immediately integrated into an European ecosystem that is there to stay until at least the next 20 to 25 years. So thanks a lot. If you are interested, get in touch either with me or Raffaele, and you are welcome to talk to us. Thank you.
Thank you very much. We have time for one question. Will you charge?
That's a really good question.
What is the business model? I mean, this is the question.
No, yeah, I mean, there will be, as in every S3 project, there will be a mixed model. So access will be based on excellence, which means that in full operation, if you want to run an experiment, there will be a competition. For the academic community, at least in Italy, and at least in the beginning, it will be free of charge at all, and definitely while a restart is ongoing, everything will be free of charge for us. The ministry is pushing a lot for making it free. For the scientific communities, of course, someone should pay. So if we don't pay, the ministry should pay at some point. But okay, it will be mostly free of charge. For non-academic partners, there could be a cost.
Okay.
Okay.
Thank you very much. Thanks again. We switch to the next session. The first speaker will be Enrico.
Good morning, everyone. So this is a presentation about media in the network. The purpose of the presentation is to show what are the current trends in media and how these are carried out in the Restart project, which essentially means fund media and other projects also using similar methodologies. This is not a presentation about AI, but obviously AI is somewhat underpinning the work that we, as well as many other people in Restart, are doing. So, when media first came around, they were a very simple thing. They were audiovisual communication over networks, essentially, and this has been going on for a long time and still is. In terms of the signal processing involved, we used to have low-level representations of the media, pixel values, essentially, on which we could do very simple operations like filtering, denoising, enhancement, very simple things. What we are looking at today is a much more complex scenario. We still have audio and video. Those are the main ingredients of immersive communications, but we have a lot more. Video is not just 2D, it's multidimensional, and so is becoming audio as well. Multiple dimensions are enabled by sensors that are measuring 3D information such as depth and creating environments that we could not use before. And besides having low-level representations, AI enables to use semantic representations to understand the meaning of audiovisual information. We are transmitting this information over communication networks having very low latency, which lends itself well to a host of advanced functionalities, as I will show. So main trends is, first of all, media have become a lot more complex. I think the first breakthrough in complex media have been 3D. This has started probably with the Kinect cameras, acquiring depth in addition to two-dimensional images. Now we have LiDAR sensors. We can create full 3D landscapes, and we can use them for augmented reality, virtual reality, as well as spatial audio and a number of other things. The other big change in media is for a long time, media have been mostly directed to humans, meaning the user, the person who watches the media, is a human being, and therefore we would optimize the media for visual quality. This is not necessarily the case anymore, as media are also being used by machines, which is what we call coding for machines in our community. So we have sensor types which are very useful, like LiDAR, as I mentioned, but also biometric data, event-based cameras, as you see in one of the video, which are not necessarily intended to be used by human beings. They are more used for inference. Inference is enabled by semantic representations, which we use for processing the data, analyzing the data, compressing the data, and so on. As this media is traveling over communication networks, we can do processing inside the network. Again, in multiple different ways, we can use digital twins to optimize the communication inside the network, the operation of the network. We can determine information about the media inside the network or on the devices and use that to decide what to do with the information that we have acquired, perhaps to transmit or to not transmit. We can learn information in the network. We can learn AI models in the network. We can also generate new media and use this in a number of different ways. For example, for what we call error concealment to, let's say, replace parts of the media that have been lost due to problems in the communication, or to generate new media to adapt to user preferences. I'll show an example of how we do this in video games, or also to create fake media and so on. So let me focus on the spatial dimensions. You know, as I mentioned, we now use 3 or more dimensions because we have very interesting sensors that allow us to create objects such as point clouds, collections of points in a 3D space which determines the surface of the objects of the scene. But by the way, point clouds also raise very interesting signal processing problems because unlike typical signals, point clouds are unordered set of points which requires very specific tools. Even if we don't have sensors to generate depth information, computer vision now allows us to generate depth 3D information for just one single view of a scene, which is what we call monocular depth estimation. And once we have this information, like one or typically multiple views of a scene, we can train AI models that are very sophisticated. Like the latest generation is called neural radiance fields. There's different types, but the main idea is you have a parameterized function, neural network with parameters theta, which you can query by point coordinates in a space, and this is a continuous model of the scene. So even if we acquire discretely sampled images, we can learn a continuous model of the scene as a function of the point in space that we would like to render and the viewing angle from the camera, and this will give us color and opacity of the scene, and we can render any view that we want in the scene. There's several different ways of doing this, but this is one of the latest trends. And the other, let's say, dimension in the communication, in the media that I would like to highlight is the emotion. Obviously, not a spatial coordinate, but emotion is the new ingredient that the media community is adding to the landscape. So obviously, the first thing we need to do is to recognize emotion, to measure emotion in some way. This can be done without using specific sensors. For example, by analyzing speech or images of faces, it is possible to determine the emotional state of the user, whether he or she is angry, sad, and so on and so forth. And this is, all the more easy if we have specific sensors like wearable sensors which acquire information that we can use, for example, about heart rate and so on, that we can use to determine the emotional state of the user. And the emotional state can be used in multiple ways. So one way is rather obvious. It is to make the communication more immersive. So we don't just have a view of the other person, but we also have a means for knowing how the other person feels. This is not the only thing, anyway, because the current state of the user, the emotion of the user, the feel of engagement of the user in a given media session can also be used for authenticating the user, because every user reacts differently to different things, and it can be used to determine whether the user is still active in that session, which is a key ingredient for continuous authentication. Now, obviously, as we acquire more and more information about the user, there's a problem of privacy of this information and communication of this information, which has to be handled. So, immersive communications have been around for a rather long time. Myself, I remember coordinating, helping organize a special issue on this on a journal several years ago. And at the time, to make a long story short, immersive communication was like big video, essentially. So the bigger the video and the more you feel engaged in the audiovisual communication. And as I mentioned, this is changing. Big video is still important, but on top of that, it is important to include emotion, sense of engagement in the communication session through all the tools that I was mentioning. One tool that can help in this regard is a digital twin. So the digital twin is a way to combine all this information in a machinery that mimics what a human being is doing, is feeling, and use that, for example, to predict how the human being will behave in the near future, and use those predictions to make decisions about how the network should work to generate the best possible quality of experience for that user. So this can be used for, as I will show, optimization of the communication process, of the video or multimedia streaming process, as well as to personalize media for the users so that they have the best possible experience. All right? So, as I mentioned, for us, it is very important to consider that media are a part of the communication process that also involves the communication network, whether it's 5G or an IP network, you know, and whatnot. The architecture that we're considering for media over networks is rather conventional, so there's not really much to say about that. We have different units. We have user terminals, which have a very limited computational power, usually. We have the edge layer in the network, which somehow may put into play slightly more powerful computational resources. And then there's a cloud where we can do pretty much everything we want. And we need to define media processing methods whose complexity is split between these three different layers so that we achieve the intended functionalities. And one important thing that I would like to mention is that, as I said before, so we're treating media in, you know, keeping into account that they have several purposes, several possible purposes. One purpose is that the media is watched by a user. Another purpose is that someone, some machine, wants to extract information from the media. And because, you know, both purposes are typically active at the same time, when we train AI models for modern media, we often have to take into account this and train with loss functions that are like convex combinations, for example, of a reconstruction loss, that is, the user should watch a video that is as good as possible, but also an inference loss. So the features that we extract from the media should be good enough that we can do things. We have a good semantic interpretation of the media that is possible by some machine learning method, by some computer. One example of this would be the recent work on the JPEG AI standard. So everybody knows JPEG. JPEG is like, I don't know, 40 years old maybe. JPEG AI is a lot more recent, and there's not much written about it that is available on the internet these days. But the idea is it's obviously an AI-based compression method which doesn't do only compression. Obviously it does compression because it's expected to. There's an autoencoder machinery that can generate features, compress them, and decode them to an image. But there's also another couple of functions that can be done. A second function is to perform a vision task on the images for which the features must also be suitable for. So this could be, I don't know, face detection, for example, face recognition, or you know, any type of inference. And the other is to perform some image processing on the features. So, for example, you might want to denoise your image during the reconstruction process, and your features should be good enough to do that. So, in-network computing can also be used in other ways. So it's not always the case that the media have to be handled, you know, watched by humans and used by machines. If you do inference on the device, you might as well decide to not transmit your media at all, and therefore save a large amount of communication bandwidth on the network. More things that are going on with the media is federated learning, so learning machine learning models in a distributed fashion among different users. And obviously, as I mentioned, as we have more information that is not just media, but also biometrics, AI models, and so on, the security and privacy, and also the trustworthiness of this media becomes important. So is the information that we are receiving trustable? Is this the information that the transmitter intended to send, or has it been manipulated? As we talk about media, about communication networks, we also talk about streaming, which is one of the typical things that we do with media over networks. And streaming can also be done for machines or for humans. In fun media, we have one of the activities is using drones, for example, for video surveillance, where the intended user is typically a machine, and there's different types of media being aggregated to perform inference. Streaming for humans means that because the media size is typically huge, we don't typically want to transmit everything. So if we can predict what the user will want in the near future, we can decide to encode just that and just send a subset of the media to the receiver. This is one of the applications of the digital twin, as I was mentioning. And the related notion is we need to be able to determine what's going to be the quality of experience for the user. Quality of experience is very important. In the past, it was essentially almost the same as quality of service, meaning the media is good if we don't have a packet loss. It is bad if we have a packet loss, and it's good if we don't have packet losses. But now quality of experience also has to take into account that there's interaction between the user and the media. The interaction can be problematic, as in the case of virtual reality, where, for example, the user can experience sickness. And it has to consider not just the audiovisual media, but also multisensory media, including touch and so on, to determine, to properly define experience. And as I mentioned, I already talked about the digital twin and its possible applications, so I'll just say the way we imagine this in fun media is that the digital twin is running in the cloud. So the cloud has an instantiation of a digital representation of a user, and the device obviously has the user, and the edge layer in the network can calculate and receive information about what the user is doing and use this information to drive and optimize the communication process. So what are we doing in the project about this? So I'll be very quick on this. I'll just give you a glimpse of what we're doing. The next two presentations by Simone Milani and Gioacchino Manfredi will give more detailed information about some of the activities. So for coding for humans and machines, I'd like to mention some activities we're doing on joint image decoding and denoising. So we're not just essentially decoding the image as in the case of the good old JPEG standard. We're at the same time calculating a better improved image. We're also working on compression, not just for images, but also for point clouds. So for point cloud compression is very important. You know, point clouds are huge data sets. They need to be compressed heavily. We're doing this in a scalable fashion. And we also have activities about coding for machines with an eye on implementation on embedded devices with very low power. So we are considering neural networks having parameters that are not defined in floating point. They're not defined on integers. They're binary or ternary, 0, +1, and -1, which obviously lends itself well to implementation, in hardware implementation with very low power. And we're considering mixed precision architectures where the low power architecture is implemented in an encoder on a device, whereas the decoder is in floating point. We are using generative models for audio to essentially perform what we call packet concealment when we have packet losses, to generate new audio that replaces those packets in a way that is semantically meaningful. We're doing this using unsupervised training, so we don't need to train neural networks. This is a, let's say, one-shot execution of the neural network. We're working on deep fakes, the problem of determining if a given media really represents the person that is intended to represent, which can be split into interesting sub-problems. For example, for the audio, where someone has just stitched different patches of audio, maybe from different speeches, to create a speech whose meaning is different than intended. And then if this has been done, which audio generator has been used, and then which features in the method were triggered by the detector to try to explain what was going on and you know, provide some explainability. So regarding immersivity, we're doing work using wearable biometrics to determine, for example, heart rate, and from that level of engagement. And we're also studying the case of multisensory media, where we have vision, hearing, touch, as well as other media, to determine what are the leading cues that are most important for the quality of experience in order to optimize the process of communication of the media. For immersivity, we have an activity in audio, generating music that is conditioned on the emotion of the user, measured as the user is playing a video game. So this is a way to personalize the content. And also for immersivity, we have an activity on demixing music during a networked music performance. So during networked music performance, we don't send individual stamps, individual audio tracks for different instruments, just one mixed track. The track can be demixed and remixed to suit the user preferences for the specific session. and also, do audio rendering in a special fashion. So this concludes the material that I had. As I mentioned, there's going to be 2 extra presentations to give more detail. Thanks.
The next talk will be by Simone Milano. Thank you very much.
Okay, thank you very much. I'm Simone Milani from University of Padova, and here I'm relating the part of the FAM media project, which is more related to work package 6, related to how we represent networked media. Okay, so as Enrico showed us, okay, in the previous talk, the general structures that we use to process this type of device is done by networks. So most of the times we use networks to process multimedia data currently. And basically these kind of structures are based by an encoder, like you have seen in JPEG AI structures, followed by several units that takes the hidden latent representation here, okay, and given this latent representation here, you can basically construct into some signals, some information which can be sent, for example, to an automatic systems, or data that can be sent to some controls. And what are the problems? Well, these types of structures have been investigated a lot, okay, during the past years, and they also have targeted to many different types of signals, like Enrico showed you, because at the moment we are dealing currently with a lot of different heterogeneous, okay, data, and also within the same types of data we can have heterogeneous characteristics. For example, if I have a 3D model taken from a LiDAR, it's very different from a 3D model taken by a depth camera, for example. And therefore, all these issues needs to be faced and discussed, okay, and dealt by the network. There are some standardization activity, like Enrico showed, so I mentioned to you the JPEG AI. I mentioned also the JPEG Plano, okay, which is dedicated to the standardization of light field images and point clouds. And basically, these 2 activities basically makes, okay, this structure standard. So in the next years, we're going to have this in most of our devices. But what are basically the problems that we have in these activities? So what to prevent, what makes so difficult, okay, the adaptation, the adoption of these types of solutions in a standard commercial device? So, like we have seen the first, Enrico mentioned the fact that we have systems that are designed for humans, so that we want to maximize and make the human experience extremely pleasant. But we also have systems which are dedicated to machines, where the pleasantness is measured in a different way. We want performance. We want to have precision, accuracy. And recently, with the advent of Metaverse era, we want something that is kind of hybrid. So we want to have both accuracy and precision and classification, and also pleasantness, because we want to satisfy multiple tasks at the same time. So you want to have images that looks good, but at the same time are easily understandable by semantic processing. And we can joke about this. We can call this meta-humans or human machine, if you want. And how can we deal? What are the problems that this poses on networks? So one of the first problems is the flexibility of the network. You cannot expect that you design one network and this fits any device, any types of network conditions, any types of user that you have. So the flexibility and scalability in these types of systems is still a research issue. And then you also have the problems of makes this network feasible. Often in computer vision you find a lot of networks which very, very high performing, very, very good generative capabilities. But the problem is that these networks are so huge that can be supported only by a limited set of devices. Is it possible to downscale this? And if so, how? And then we need also to adapt the network to different conditions. For example, how does it work if I combine images in a federated learning setup taken by drones with images taken by cars, with images taken by drones in a foggy environment in a different day? So this diversity is one of the key elements that we need to face in these applications. And then we need to deal with generativeness in the sense that we're going to have more and more fake or, well, generated contents, okay? Not simply fake, but generated contents on the network. For example, currently, most of the phone vendors, most of the AI vendors are provided users with personal digital twin. It means that in the future, you can phone me and probably it's not me answering, it's my digital twin which is answering your call. And still, this is an issue that is still be possible to have in the next future on your phone. So, how to deal with this? So first of all, we tackle the problem of scalability, of flexibility. We want to optimize the quality that we have with a specific network. And this is a problem if we consider, for example, this structure here, which is the structure of any standard point cloud coder or image coder based on learning. Okay? So you have the first network here, which is what also Enrico showed you before. But on this network, you basically build a probabilistic model that is used by the entropy coder to minimize, okay, the amount of bits that you transmit to the specific stream. And like Enrico showed you, you have that these elements are optimized considering a target function that combines the fidelity, so the similarity between the input and the output, together with the bit rate, so weighted with the bit rate that I generate. This means that if I train this for a specific target bit rate, well, I will have one configuration. If I change the target bit rate, these weights, this configuration, these parameters change completely. So changing bit rate means changing network, changing weights, sometimes changing also the number of parameters that you have, because you have completely different setup. And you think about a device that needs to switch from one bit rate to another, this can be a strong issue. So how can we solve this? That is the main challenge, one of the challenges that is not posed by most of the systems. So we can solve this by basically noticing this. So if we train the different bit rates, or different rate points for networks separately, I got this. And I check, okay, the latency, I computed the correlation between the latency that I generate, I have this. So latencies are completely uncorrelated. The different numbers here are basically different rates, 1, 2, 3, 5. Okay, different rates. Latencies are not related to each other. But if I do a progressive training, it means that I train my latencies on rate 1, and then I use this partial information to train rate 2, and so on. You can see that latencies are correlated quite good. This means that I can build networks to switch from one rate to another with only a few additional bits. And this is basically the structure that we have designed using, okay, in collaboration with the EST Lisboa, and it's been built on the top of JPEG Plano point cloud coding. It's a structure that basically allows you to switch from one position to another with only a few bits by adapting the entropy coder and therefore allowing you to reconstruct, okay, the input information at a higher quality. This is a very generic scheme. It has been adapted on point clouds because point clouds are really a hard task to code, but it can be adapted to any media that you like. And the nice part about this approach is that here on this green line, you have basically the independent coding, so scalable independent coding using JPEG PCC. And if you use our approach, you have a better performance, which are very close to the black line, which is non-scalable, okay, solution, non-scalable configuration. So what I'm saying that if you do scalability properly, you can have the same performance on non-scalable coding. And sometimes you can also have a better performance. Just look at the red line, because by doing this progression refinement, you have that the quality and the noise can be removed. And therefore you have a better performance. So, together with this, you can say, okay, I have standard features. So my features here have been designed by the committee that designed the standards. Is the quality defined? Well, no. What you can do, you can put some more effort, some more advanced decoding effort at the receiver in order to improve the quality of the scheme. In this work by University of Brescia, we have that the use of a decoder which has been empowered by a transformer structure, is it possible to start with a standard bit stream? And then by adding extra complexity, you can have a higher quality and reduction of the noise. So what you're doing decoding and denoising at the same time. And this allows you to solve the system very quickly. Solve define different quality for different people. Finally, we also have the problem of transmitting the networks to devices that are extremely low power. And this is the problem of compressibility. So together, the Polytechnico di Torino has designed systems that, like Enrico anticipated, is defined by defining weights by 3 values, 0, +1, -1. So this means that I can reduce a lot of nodes in the network, the 0 elements, and I can also implement the operations by simple summation and subtraction. And this has been ruled by this parameter here that change throughout the network. And the results that has been displayed here shows you that you can have a compression of the network about 90% with only minimal loss. At the moment, we are developing this, and we have one paper that is going to be submitted this month on waves, that is going to show you that it's possible to use this for biometric system and biometric signals with just 1% loss, but an extreme reduction of complexity and size of the network. And finally, we have the problem of how we can ensure with these features, the validity, of the signal. Is it possible to verify if the signal is generated or not? And the work done by Politecnico di Milano basically exploits multiple types of features, typically from the audio signals and the video signals. We infer some emotional elements like the prosodic characteristics, the use of facial mimic attention, and then using these elements, combining together, it's possible to verify whether, the face is authentic, or if the video is authentic, or has been edited by some deep learning structures. More precisely, they have discussed the possibility of fusing video and image features at a different level of the networks. And what they have seen is that if you are closer to the initial layers of the network, you have a better performance. So finally, I can conclude the talk by showing you or stating that the features can be good for some tasks, but if you want to have features that are highly flexible and can be deployed on a network media, we needed to do some adaptation. So you needed to include flexibility into the architectures. And this flexibility must take into account networks, the originating device, also the processing hardwares. Also, the consistency with the different types of features is a problem, but still there is a new problem for the future. So how much this consistency will stay a resource, for example, for the validity check? Because still networks, deepfake networks are evolving, and it's possible that these inconsistencies that now are a resource can be not a resource anymore in the future. And moreover, another thing is that how we can ensure and embed issues like privacy-preserving networks and digital rights, issues like, for example, problem with the fairness and biases into these types of solutions. So these are basically what we're going to investigate in the next months and in the next future, so we hope so.
We have time for one question. Okay, I have one actually. It came when Enrico was talking. It's about emotions, right? Because on the one side we want to transfer emotions, on the other side we want to preserve privacy. So I mean, furthermore, one of the things that we say is that humans are able to understand other humans. Now it looks like this paradigm is sort of exploding, right? It's disappearing, or You know, how do you think that all these three things can, in this triangle, fit all together?
Well, actually depends what you are using your emotion for. If emotion is used to have a better response by an automatic system, you need to send only the information about the emotion, not my identity. So the network can be designed to send emotions, but preserve, avoid any leakage about your identity. If I needed to, let's say, communicate with you from remote because I want to have a better human experience in our talk, for example, there is no privacy issue. It is you.
Okay. Thanks a lot again. So the next speaker will be Gioacchino Manfredi.
Good morning, everyone. I am going to talk about the last part, and in particular about innovative audio and video streaming strategies to improve the quality of experience of users, where by quality of experience, we, as already said, we mean the degree of satisfaction that a user perceives when consuming a multimedia content. In particular, I'm going to introduce two recent activities, and the first one concerns the control of a swarm of UAVs equipped with cameras streaming images to a central ground station for video surveillance. And the second activity which actually has been carried out by my colleagues at the Polytechnic of Milan, proposes some audio signal processing techniques to improve again the quality of experience of users for remote user interaction applications. So now, regarding the first part, we have focused on the problem of decentralized control of UAV swarms for video surveillance. So basically, the scenario is a swarm of drones that have to surveil, so have to cover an area. They are equipped with cameras that are able to capture images on the ground, and then these videos are required to be streamed at a central ground control station. Now, what we also require is that obviously these videos should be sent at the highest possible resolution, and we also require that the coverage of the area is highest possible. And another very important requirement is that these covered areas, let's say the areas scanned by each drone, are overlapped. So they should present, let's say, satisfactory amount of overlap. And this because once these videos are streamed to the ground control station, they can be, for example, fed to stitching algorithms to make a unique video out of all those single videos. Now, the approach adopted is a leader-follower multi-agent system leveraging model predictive control. And so, in particular, we have the leader following, tracking a predefined path, and all the other agents trying to stick together, and so present in such a way to have this amount of overlap, but also trying to follow the leader, obviously. So now the main problem in this case is, again, the network available bandwidth, because as we know, the bandwidth is not predictable both in time and space. So what one can do is just use one of the congestion control algorithms to try to estimate the available bandwidth in that specific point at that specific time. And we want to do this because, as we said, the videos captured by the cameras have to be streamed at the ground control station at the highest possible resolution. So, in other words, we are requiring that the quality of experience, now measured in terms of, let's say, visual quality, is the highest possible. Now, so basically the idea is that when we have high available bandwidth, the drone altitude can be high. So in other words, the drone can get far from the surface, and so the scanned area can become wider. And this because the drone can afford to stream the video at a high resolution. So even if the drone is far from the surface, the images sent will have a high resolution. On the contrary, as it is, let's say, logical to think, the lower the available bandwidth, the lower the drone altitude. So, in other words, in this case, the video streamed will be streamed at a low resolution. And so, what the only thing that we can do is to get close to the surface in such a way that we can increase the visual quality of what we are seeing. So, the control methodology adopted to do this is nonlinear model predictive control. And in particular, each agent runs its own model predictive control, basically having two states, the tracking state and the recovery state. The tracking state, it means that we have an acceptable amount of overlap, and so everything is okay. So the leader can track its own reference path, and all the other agents can stick together, can follow the leader, and also the reference height, which obviously depends on the available bandwidth. And there are some cases, however, where let's say there is no longer an acceptable amount of overlap between the scanned areas of the drones, and so in this case there's a risk of detachment. So in this case we switch to the recovery state, where the leader stops to allow all the other agents to catch up with it and also to stick back together. To get, let's say, to have a better understanding of what I'm saying, let's just look at the figure on the right, where we have the X and Y coordinates of 5 agents performing the task I have just described. And so the white bands describe the tracking state, while the recovery state is represented by the gray band. And what we can see is that at the beginning, in the tracking state, the X and Y coordinates are quite close to each other. And so this translates in an acceptable amount of overlap, as we will see in the next slide. But at a certain point, these coordinates start to get far from each other. So the risk of detachment between the scanned areas become high. And so the system switches to the recovery state, where the leader stops. And we can see this because the leader is the thick blue line, and so this line becomes basically constant. So it stops to allow all the other agents to, again, get closer. And as this happens, they switch back again to the tracking state. And so the leader starts moving again, tracking the reference path. Now, this is, let's say, one of the simulations performed, and the video shows these rectangles. Now we can see these rectangles represent, each of them represents a specific drone, and these rectangles are basically the areas scanned by the cameras, and where the blue rectangle is the leader and all the others are the followers, and the dashed line is the reference path that the leader is required to follow. Now, what we can see is that as long as there is an acceptable amount of overlap, the leader will move, will go on, and so all the other will follow. But as soon as there's a risk of detachment, the leader will stop to allow all the other agents to catch up. And we can see this because now, if you see, we are now the leader starts tracking the path, so we are in formation, which is the tracking state. And so at a certain point now in the band, we can see that all the other agents rearrange their position, but then there's a risk of detachment, and so the leader stops, goes into the recovery state to allow all the other agents to catch up. Obviously, you might have noticed that the areas of each rectangle change over time because of the available bandwidth. And so in other words, we are saying that the altitude of the drone is changing over time. Now, going on a step further, that is currently being studied and analyzed, is to drop the hypothesis of having a predefined path, because basically, and we are turning to the more realistic case where we have an area that has to be scanned, that has to be covered and monitored, and so and the swarm of drones that has to fulfill this requirement. So in this case, the leader knows the position of all the other agents, and so is able to compute the overall area scanned at a certain time step. As we can see from the figure on the right, and in particular from the orange line, that is the overall scanned area. And so now we designed an online path planner that, on the basis of this specific area on other parameters, and especially on the map of the environment, which for the moment has been supposed to be obstacle-free, computes the next reference point to provide to the leader. And so the leader has to reach this reference point by running its own model predictive control, and all the other agents has to follow the leader as already described. And so at the next time step, the procedure is iterated and so on and so forth until the end of the task. So all these simulations show what is contained in these figures. So on the left in particular, we have a rectangular area that has to be scanned, which is the area inside the blue bands. And now the light red area is the area covered by a swarm of 3 drones starting from the top left corner and going on. As you can see, the online path planner is inspired to the lone mower technique, but this is, let's say, more aware because it is aware of the area already scanned by and already covered by the swarm. And then the thick red line is just the union of all the reference points provided by the online path planner, where those points, the points are just some of the reference points computed. On the right, basically, you have a similar simulation, but we have plotted the overall scan area at each time step. Now, regarding the second part of this presentation, let us consider the case of networked music performance, where we have musicians collaborating or rehearsing in real time from geographically displaced locations. And so in this case, obviously they need the audio track to be performed in real time in order to obviously collaborate. And so, but unfortunately there are some challenges such as network latency, data loss, etc. And so there's a need of designing specific audio signal processing algorithms. So, and in particular, it is known that packet switched networks are prone to packet loss. And so to this end, packet loss concealment techniques have been designed to, let's say, reconstruct those packets that have been lost in real time. And to this end, ParkNet has been proposed as a novel technique that is based on a feed-forward neural network that is able to, let's say, predict the received audio track, and so to reconstruct the packets that have been lost. And the results shown in the figure on the right, with respect to the other state-of-the-art approaches, show that ParkNet actually outperforms all the other approaches, so is able to reconstruct and so perform packet loss concealment in a much more effective way. Another aspect, as already mentioned before, is online demixing. And this is particularly important because online demixing algorithms allow to decompose an audio track into single elementary stems in such a way that then each user is able to remix these single tracks according to their needs. A particular step forward in this direction regards drum audio tracks. So in this case, we have a drum audio track.
2 minutes.
Yes, sorry. We have a drum audio track, and so these audio tracks basically have to be decomposed into the 5 elementary pieces of the drum. And so to this end, the largest data set to date has been built, and we have used this data set to build LastNet that is able, given a drum audio track, to decompose efficiently and real time the 5 pieces of the drum. Now, another important aspect, always regarding networked music performance, is the sense of presence. So, in particular, convoluting the audio track with the reverberation. And so, in this case, instead of making the convolution that cannot be performed in real time, the idea is to design feedback delay networks that approximate such a convolution in real time, given a specific audio track and a specific room impulse response. To conclude, some other solutions regarding immersive networked music performance have been proposed based on leveraging software-defined networking and multi-access edge computing capabilities of 5G networks, along with machine learning techniques to predict the traffic and also to perform packet loss concealment, as already described. So thank you for your attention.
Thank you very much. Thank you. Okay, so we are starting the new session. It will be a 1.5 hour session. Okay, we will have 4 talks. We want to give a clear message that we want to proceed on some topics as a program as a whole, and so we decided to have this. We are presenting ourselves in the same table. So anyhow, the first speaker will be Riccardo Marini.
Okay, welcome back. Welcome to the session on network digital twins and infrastructure platforms. So my job here is twofold. First thing, I have to catch your attention after the break, which is never easy. Second one is actually to introduce, as Giacomo was saying, the talk that you will listen to in the next hour and a half. The idea is that we have, let's say, we want to go through the topic of the digital twin and infrastructures, as the title says. But starting from a general perspective, I will give a brief talk on why do we need a digital twin. And then Giacomo, Marco, Roberto and Lorenzo will go through the details of these activities that we are carrying out within the Grand Challenge and different restart projects, so that we will move the focus from the digital twin towards the infrastructure at the end of the talk. So, I don't know if you noticed, but this plenary has a payoff, which is how will the future look like? I don't know how the future will look like. Actually, I don't know if any of you knows if how the future is going to look like, but anytime I have a question, I don't know what to do, I don't know what to do, but I ask ChatGPT. And ChatGPT gives this very beautiful answer saying, okay, the future is bright, fascinating, there are a lot of subjects that we will invest in and grow up. Okay, fine. Which are these aspects? Well, there are 4 main topics that ChatGPT is telling you that will grow in the future. The first one is technology and innovation. Of course, he understood that I'm an engineer, and that's the first answer. Then, of course, start talking about environment, society, and health. There are a lot, let's say, of important topics here, but we want to focus on the first one. And if you go through that reply, basically you see that it's talking about 5G and wireless communication. It talks about 5G expansion, whatever it means. Talks about 6G, okay, fine. Talks about quantum technologies, okay, and AI. So let's try to go a little bit deeper in what ChatGPT thinks. This is a very huge wall of text that I'm not going to read, but the first thing that came up to my mind when reading this text is that there's a word here, or at least as an expression, which is repeated most of the other words. I highlighted this for you, and it's digital twin. So ChatGPT thinks that the future in the telecommunication world will be dominated by the digital twin. Fine. If I was able to know how the future would look like, I would have known that yesterday everyone talked about digital twin. For example, in the network AI session, the word digital twin was said at least 15 times. Today, we talk a lot about digital twin. So I don't know if someone was talking with ChatGPT when we defined the Grand Challenge initiatives, but of course, this, let's say, says a lot on which is the importance of digital twin in our all activities. So we started this, let's say, we kick off this Grand Challenge in May. We had 3 meetings as of now. But I always like to remember that the Grand Challenge initiative on Digital Twin actually started a little bit before, because we have a panel on the scientific track of D5G and Co this year, D5G and beyond, where we had two very interesting talks from two players from the industrial ecosystem, which is Team and Wind in this case. So they talk about their vision of the digital twin and the network digital twin. They talk why it's important to develop, let's say, and move the research toward these activities. So let's say that in this very day, we, let's say, put the first brick on which is the activity on the digital twin that is carried out throughout all the Restart program. From the workshop to the Grand Challenge. The idea is simple to be written on a slide. We want to have impact. Every time I participate in a plenary, we say that Restart should have an impact. We should go beyond just completing the projects, writing paper, but we have to, let's say, do something. So the idea here is quite simple. We want to have impact. How? We want to help the operators and, in general, the industrial ecosystem to set up tools which may facilitate the management of the network through digital twins. And so let's say that the idea that we have here is twofold. At first, we want to understand how we can integrate the digital twin within the existing telecommunication infrastructures. And that's, let's say, easy to say. Second aspect, we want to create a framework which is able to manage digital twin and a federation of digital twin. Because, of course, we have to take into account the fact that every player in the ecosystem may be interested in developing its own digital twin with its own capabilities, its own activities. So the idea is that how we can somehow make these digital twins talk with each other so that the effort that we put in these activities is common through the entire Restart program. This is the list of the Restart project that, as of now, have been actively working in the Grand Challenge. They participated in meeting. Of course, these are not the only projects working on digital twin throughout the Restart program. So I encourage every PI of the project, every participant of the project, which is not, let's say, involved in the Grand Challenge as of now, to text me, to write me an email, to be, let's say, part of the activities that we are trying to develop. And starting from these projects, we try to understand which are the, let's say, tasks, activities that each specific project is carrying out within the Restart, within the digital twin framework. So we defined a set of tasks, let me say, which go from basically the definition of a general reference architecture for a digital twin. And okay, I'm not going to go through them, but basically we will like to reach a point where we can actually develop some testbed in collaboration with the operators, in collaboration with the industrial ecosystem, to see this actually come in reality. We tried also to, let's say, give a schedule to these tasks so that basically each project, let's say, is able to contribute to the Grand Challenge following its own activities. And you see here that there is a red line which is, let's say, indicating the end of Restart. This is a message because we think that this activity is very important, and since this activity is very important, we think that we should find a way to go through the rest, or to go, let's say, after the Restart program and keep working on this topic, because again, the idea here is to have an impact, and to have an impact, we have to produce something which is actually can be useful to operators. I'm gonna go through the very first one, and then a couple of things about the last one. Then, of course, Giacomo and Marco and Lorenzo will give you more details on the, let's say, singular activity that we are carrying out. But let's say that for defining the reference architecture, we started from the, let's say, IRTF standard. Maybe this is something that some of you are familiar with. Let's say that this standard define a physical network, which is, let's say, physical network layer, which is the actual network, an application layer, which is the way the user interacts with the digital twin, and the actual digital twin layer, which is made, let's say, of some components that I will discuss later. The idea is that starting from this architecture, we want to give a unique perspective of which is the vision of Restart in terms of the digital twin architecture. So in this sense, the coherent project made a huge step, defining some sort of key target feature which should be taken into account when defining the architecture of a digital twin of a network. Basically, you see here that these key target features are the composition, because, again, we are talking about a possible federation of digital twins. There are many entities that collaborate throughout the creation of digital twin, so that's the very first step. Then, again, we have to corroborate this fact by accounting for interoperability and federation capabilities. We want this to be a service-oriented architecture. The coherent project, let's say, investigated to the definition of the Restart digital twin architecture. And I was talking about the service-oriented architecture, because of course we have to take into account the fact that this architecture should be oriented to exposing services to users. Finally, we should follow the paradigm of this intent-based networking, which is, again, a trend that nowadays is quite spread across all the research activities. And finally, we want the orchestration to be driven by a module which is capable of simulate and predict which will be the behavior of the network and how we can interact with this digital replica to actually change its behavior and understand what is going to happen. Besides making a figure which is quite nicer, I would say, we try to understand, let's say, how we can incorporate these key target features from this IRTF architecture towards, let's say, a view that we have in Restart. So let me just go through very briefly the different components, which you will see they're quite similar because we want to be as compliant to the standard as possible. Starting from, again, the physical network layer, which is the actual physical network, which is going to be communicated with the digital twin layer, sending data, because of course, to create a digital twin, you need actual data, real data from a network, and receiving control messages, which will be used from the digital twin layer, and so from the manager of the digital twin, to actually communicate and do something on the physical network layer. And again, we have an application layer, which is the way with which the user will interact with the actual digital twin by addressing the services which the digital twin layer is going to expose towards the user, and receiving this intent injection, which will be basically a way to translate the policies, the complex network policies that are commonly used to manage the network from, let's say, a more general input from the user side. Then we have the actual digital twin layer. So basically we have this digital hub, which in a sense is a big digital twin. Each entity is going to have its own digital twin. So basically a single digital twin may be made by different components, which are the actual DT blocks that you see in this blue box. And we have a number of digital hubs, because as we said, we are accounting for the fact that we may have a federation of digital twin, where different players may want their digital twins to interact with each other. Of course, we have a data repository, because we have to store data somewhere, and this comes with a lot of issues related to security and everything consequentially. And then we have this digital twin manager, which is, let's say, the component which is actually dedicated to managing the digital twin using this simulation and prediction module that I was referring to before. Finally, there's this service marketplace and intertwining manager, which is dedicated to exposing the services which are available to the users and managing this intertwining, let's say, feature that let different digital twins talk with each other. A couple of words about possible use cases that we see in different Restart projects. First one, for example, is an activity that we are carrying out at YLab in collaboration with team, which is dedicated to the optimization of the coverage and capacity of a network using AI tools that, of course, may interact with the digital twin to actually change and enhance the behavior of the network by accounting for the condition of the network itself. For example, developing some methodologies to predict KPIs that user will expect. Or on the other end, there are some, let's say, scenarios that are taken into account within different Restart projects. For example, the in project, which is dedicated as Lorenzo will discuss later, to industrial networks, envision the possibility that a digital twin may be used both for indoor and outdoor scenarios to basically control and manage a network in this very specific scenario. For example, having some, let's say, simulation capabilities of the introduction of drones or mobile robots which are moving in the environment, as well as for the very first case, manage the network itself by getting data from the network and making some changes towards some specific KPIs that for some specific time intervals should be fulfilled. Or finally, of course, smart city scenario. For example, there are other projects such as 6G YNet, which are dedicated to this kind of scenarios. And of course, having a model which is able to, for example, predict the urban mobility and then optimize the network to match this kind of prediction may be useful. So this was just to give a hint of what we are doing in the Grand Challenge, what we are discussing in our meetings, and what the different Restart projects are doing. Again, Giacomo, Marco, and Lorenzo will give you some more details on the activities. Let me just finish with this slide, which I usually take as the very first slide of presentation I give about the digital twin during, for example, the Grand Challenge meetings, which are the, let's say, the takeaways that we discuss at the 5G and Beyond workshop, but which I guess may be used in this, let's say, location to describe which are the actually pillars of what we are trying to do within this activity. I tried to explain why the digital twin are important. Of course, they are a key factor for sustainability, data-driven innovation, and okay, we can agree on that. Of course, they may be, let's say, useful for different applications. You will see that we're gonna talk about smart city in industrial scenario, but in general, as you saw during all the presentation of the, let's say, the other session, we had a lot of digital twin popping up now and where. And then, of course, I didn't touch this point too much, but it's very important because if we want to go for a federation of digital twin, we need to take into account the fact that data should be shared in order to let this digital twin talk with each other. But finally, the thing that I want to highlight is that the Restart program may actually be the catalyst to do something in this, let's say, in this objective, because we have a lot of projects, we have a lot of activities on digital twins spread across all the projects, but we should try a way to cooperate, to find a way to cooperate and build a common framework that may be used to, at the end of Restart, maybe have something that we can say and basically talk about as this is an output of the overall Restart program. And this is, for example, how to create a digital twin of a network. Thank you.
Good morning, everybody. It's a great honor for me being here. I'm Marco Beccattini, and I am here to introduce you a higher level view on the concept of digital twins, and especially for digital twins for network, and to understand their value as we see them as strategic elements for the evolution of the network panorama. I know this is a very bold statement, but what has been asked us is to be bold. And I really appreciate this from Restart that asked us to go through the hurdles and challenges to create new perspectives on the future of networking and telecommunication. So we ask ourselves which might be relevant challenges where we can put the bar and trying to make our work the most evolutionary as possible, transformational, at least in ambition. So we outline several objectives. They have been declined differently today, but if you see, they go on insisting on the same points. We want network to be more autonomous and more flexible. We can call it the zero-touch approach, the low-code, no-code approach, the high-resiliency approach. We want to introduce element that goes under the umbrella of KV management. It is essential that networks manage ethical values which also refer to economic dimension. Let's think of the relevance of the consumption of non-renewable energy. we, as Giacomo before explained very well, thanks him, that we need to surpass the complexities of interfaces, going towards an approach which is deviceless and serverless, which means that the community of developers should focus on functionalities and not the complexities of the interface. And last but not least, and at least for now, one of the most important elements, we need to address how we can bring high computational capabilities within the network. In network computing, and especially in network artificial intelligence, will be the frontier to understand if network providers can expand their services, or if those services will be provided by over-the-tops that probably, as it was said yesterday, will finish in taking control of a big quota of the network. We understand that this is ambitious, and we would like to focus that Restart, even if it has a very tight-in connection with European and worldwide project, is an Italian project. And as Italian, we really find that elegance is one of the key characteristics of our engineering. What is an elegant solution? It is a solution that can address several different problems with a tool. The simpler and most effective the tool, the better it is. So we are trying to address those challenges that we said before with few key concepts. And the concept, if we look it from an engineer perspective, is that we need a tool that gives us the capabilities to move from the edge to cloud continuum, to be able to tap the characteristic of each of one of these type of deployment. Low latency on the edge, low cost on the cloud. Large data on the cloud, specific, relevant, but raw data on the edge. On the other perspective, like specular, what we have is that we need to be able to address the very asset, as with the asset administration shell interface, which allow us to interface directly with the very edge element, the antenna, the server, the router, MEC, with the capability to have an abstract, high-level view, what we call the meta model. So, since this seems at least a good landscape and good perspective to understand how we can address those challenges that we listed before, we started to think which might be a tool that allow us to go toward this perspective. Digital twin seemed a good candidate, and we start to invest in it. Digital twin as a concept is born in the industry. The idea is to create a high-fidelity representation of an industrial asset. But as you can see here, we have been a lot of evolution of the concept of the digital twin. And staying on the point of being brave and being bold, we thought that maybe we could extend this concept. So we did not want to work with digital twin, but we want to work with the concept of a digital twin of a telecommunication network. We start specializing. So even if there were a lot of concepts of interconnected digital twins, which might go in literature under the name of digital twin networks, we are building a digital twin of the network, which are similar but differentiated concepts. Thank you, Claudia. We have been discussing this a lot. The other evolutionary element that we have been discussing is that we need a hierarchical system of digital twins. In an industrial scenario where there are not so many concerns in terms of energetic consumption or latency, it is okay to have digital twins that fully replicate the whole asset landscape. But in a network, in a telecommunication network, in those scenarios as complex as in Europe, it's not possible to imagine that we analyze every time all the network in its complexity. So we introduce layer. Each layer provides a more stylized view, but at the same time, this stylized view allows for new services, a new perspective on the network to be investigated. Our grand challenge is provide new network service via digital twin. This is the approach. Each level of abstraction allows for different services. At low level, we can reconfigure the network, but at high level, we can ask how we can make our national network more resilient to foreign attack, more compatible with renewable energy goals. So, as you see, combining those two perspectives, what we can have, what we can do, is we can have a plethora, a multiplicity of digital twin representation of the network. We can have a low-level, high-fidelity representation, which are very connected with the very structure of the network, and we can have more high-level, more abstract representation, which are more connected with high-level KVs, or strategical view of the network. This allows us not to have a single digital twin representation of the network, but multiple digital twin representation of the network. And this is one of the key elements of our proposal, because this way we can have, in the same time, multiple representation of the network that are run contemporaneously along the edge-to-cloud continuum. This allows to face, for example, what-if scenario strategy assessment. What would happen if the network was this way or this other way? How my network can sustain a given traffic or a given challenge? And so what you can ask me, and I think this is a very sound question, is, Marco, but how we can do very complex what-if analysis due to their computational cost? And here we have all the advantages of working with models. High-level models, if designed well, can provide us insights on how the network will behave, but at the same time doing this at a very low computational cost. And we have been prototyping this, and this works. So here the question might be, and how this scenario that you show us works? Well, it works in a continuous cycle. What we have is that we have the physical network, the real network. The real network is probed, and a high-fidelity representation of the network is created. Then, according to our strategic needs, we create more high-level views with different type of gathering, different type of sets, what we are called digital twin hubs, as Ricardo very well explained before. These allow us to run models. Models with probabilistic or quantitative methods allow us to choose which are the best configuration for the network, and then we inject those configurations within the network via the southbound interface. And the cycle never stops. This way, we have feedback on how we are working and a continuously update view of the network. All I said before can be conceptualized in this schema, where we have the physical, which is the current network configuration, which is related to the view of the network, which we call the operational view. Operational view is abstracted in model, which constitutes a repository of potential configuration of the network, declining different level of accuracy. which are called knowledge. And on this knowledge, we can run strategic analysis on the basis of which we choose the best configuration for a given scenario. And if it's necessary, we can put them back in the physical. This might seem a little abstract, but here it's very helpful, the presentation of Riccardo before, because we can show that each one of these elements is mapped on the reference architecture we are working on. And specifically, as you can see, the physical layer maps, obviously, on the physical layer. The operational layer maps on what is called the support system, which Giacomo has explained before. The knowledge belongs to this area, which we call the marketplace, because it's a market of all the possible application of the network and the configuration which enables this application. And the strategy, which is how we can investigate those configurations in order to understand which is the most fit. We have been prototyping, as said before, this approach. And for example, we are able to apply quantitative methods of subset of the network, as shown on the left, to understand, for example, how reliable a network is, or how a network with a given configuration corresponds to demands of, for example, ultra-low latency, ultra-reliable network, which are very important in industrial setting, for example. We have made a paper with Bologna on this. And so, as you see, this approach seems and is very promising to address the objectives we listed at the very beginning. But this is not enough for us. What we want to is to create, and Giacomo showed this before, a further evolution which can leverage the latest development on the AI field using artificial intelligence to promote the use of artificial intelligence, to enhance partnership with other projects, and Crown Challenge is a very useful for us scenario to create this network within Restart. And we would like to extend current networks. This is an objective that we have with industrial partners. We have a very strong relationship with Windtre, our thanks to Windtre. We know that Bologna has a very strong relationship with TIM. Altogether, I think we can do good. We are a great team. I really thank Restart for this, and everyone to join is welcome. Thank you for your time.
Thank you, Marco.
Hi, everybody. Good morning. Mine will be a very quick presentation. Actually, the scope of my presence here is just to introduce to you Lorenzo Morosa, who is the speaker for this last slot of this, yes, please, of this session of the meeting. Actually, though the scope of the session was digital twin of networks, in fact, we wanted also to give some insight on the status of this project. I'm the PI of it, which is in industrial networks, which is one of the most vertically oriented projects of the entire Restart program. In fact, it is dedicated specifically to the Italian automation industry and to the way communication systems can enable new use cases in industry. So the concept of digital twin of networks is one of the many concepts that we analyze in the process. So in the next 25 minutes, you will have an idea of the different aspects that are discussed in the project, a project which, being very much vertically oriented, as I said, of course is publishing a huge number of papers, but more importantly, is working in order to create a number of POCs, or proof of concepts, next year in 2025, which will be the way, the most important way we will measure the impact we're going to have on the future of Italian automation industry. In fact, I want to emphasize that through the Cascade call, we had the opportunity to have new partners included, and overall now it's 14 plus 1 partners, where the majority is companies, and this is because we want to make POCs, and some of these new companies which are entered have as a specific goal the support to the topic of digital twins. This is the WBS of the project. I'm not going to read it. What I just want to mention is that we have a very integrated view. Of course, when you build a POC, you have to put everything together, the file layer, the network layer, the network architecture, the data analysis system. So it's very much integrated. We have already identified 5 major use cases, each of them basically providing in 2025 a POC or even more than one. The concept of digital twin of networks is one of those who have been analyzed through this integrated process. But actually, as I said, the scope of my presentation is just to introduce you Lorenzo, who is a PhD student last year, PhD student at the University of Bologna, deeply involved in the IN project. And in fact, now, in the next 20 minutes, he will provide an overview over some activities which are tightly connected, which actually point to different WBS. So his presentation is a good example of what else we do within the project beyond the development of the concept of the digital twin of networks. So I give the floor to Lorenzo.
Thank you, Roberto, for the introduction. Okay, good morning, everybody. As Roberto has introduced, today we are going to see in more detail what we're doing inside Restart In project. And in particular, we can see here how digital twins are deeply coupled with AI. And also, there are many, many ways in which we can pursue new research directions in order to achieve interesting and successful goals. So I'm going to talk about towards AI native industrial networks in details. So, first of all, I'll give you a quick look at what we can do currently with current standards with 5G, some proof of concept, so basically, in industrial setting and industrial IoT. And after, we will see how we can think of AI native networks. So in particular, we will see some examples about federated learning in industrial networks regarding topics about security and topics about goal-oriented communication, such as importance-aware scheduling. So basically, let me introduce you this use case, this proof of concept, that is about remaining useful life estimation for an industrial use case and industrial IoT. We have this mobile robot, and this mobile robot is doing some operations inside a factory floor. Basically, for example, it has to carry, for example, some liquid from a point A to point B. And there may be some obstacles within the environment, and the robot has to react to this obstacle in a predictive manner. So it has to avoid, for example, the spillage of waters from itself. In order to perform this monitoring, we need, first of all, the communication network, so a very efficient 5G architecture, for example. And we can think of a private architecture, for example, because we can have, within the factory itself, we can have a 5G private network comprising the RAM part and the core network. And inside the factory itself, we can also have, of course, the server, which can provide functionalities to host the AI models to predict and forecast failures in the system, so it can react, the system can react, it can avoid the spillage of liquids from the mobile robot. So I'll quickly show you a video here of this proof of concept into action. So basically, we can see here the mobile robot, which is equipped with some sensors and some devices which provide functionalities to connect within the private 5G network. And we can see the bottle of water with a grip which can hold it in case of a fault. And of course, we are mentioning digital twins, so we can also monitor this set of information and data we are collecting, for example, acceleration or gyroscope data from the AGV. We can monitor the position of the AGV of the mobile robot within the factory floor itself. And we can track what's happening and monitor its behavior. We can keep track of, for example, also of the orientation of the AGV. So we have all the information, all the useful data in order to have insight about the behavior of the mobile robot. And then we can also see that this is, of course, the user equipment that you can see on the mobile robot, while we are communicating with this private infrastructure, which is provided by Team, and which is helping us to deliver AI services. So without AI, in case there is an obstacle, there may be a fault, and basically what can happen is that the water can be spilled from the AGV. But in case of a system which is featuring AI, we can try to send sensor data to the service, to the server, sorry, and then when there is an obstacle which can provoke the fall of the liquid from the AGV, then the AI can act and can interrupt this spillage, basically. So this is a proof of concept we already have in Bologna, and we're already working within the project of Restartin, and we are working on this in order to exploit and understand better what can be done currently with new technologies, with current technology like 5G, and next future technology like 6G, the one towards which we are working on. Okay, of course, we have considered that for this specific scenario, we have a specific configuration. We have a private network, we have all on premises of the factory, but of course that is not the only case we can consider. We can consider what changes if, for example, the core network is a public infrastructure, or what changes if we change the operating frequency FR1 to FR2, for example, in 5G settings. And so this, we can analyze in an end-to-end fashion what changes if we consider the communication part, but also we can consider what changes when AI, when we consider different AI models. Because AI, we know, is not a black box. We have to open that, understanding what changes if we use a convolutional neural network to predict if a fault is about to occur, or another deep learning model such transformers and so on. And we can see with this table of results that, for example, for this specific use case, convolutional neural networks are quite effective because they can analyze time series data handled by sequences. And in particular, we can see that in terms of false negative, false positive rates, or anticipation margin, basically how much time the AI provides in order to avoid the spillage, the CNN, the convolutional neural network, is the most performing model. But then we are interested in also in the overall picture. So what's happening in the overall system? What's the most, where does the delay come from? For example, we can see in this plot, according to the number of mobile robots on the x-axis, and according to the round-trip time needed to perform the overall communication in uplink and downlink in order to avoid the spillage of liquid, we can see that the most important part in the actuation of the prediction of the spillage of liquid is not in the network itself, it's not in the 5G network itself, which is quite efficient. We can see that the delay introduced by the core network, which is the blue component, and the red component introduced by the delay introduced by the RAN network, are really, really negligible with respect to, instead, the time required by the AI itself running at the server. So also on a good performing, enabled by GPU infrastructure. And most importantly, the actuation part that is needed for the grip to block the water bottle. Those final two components are the ones which are requiring I would say, the most time, in which are introducing the high delay in the system. So we are interested in this project to understand the overall infrastructure in an end-to-end manner. But now I want to discuss something which goes beyond this, because basically we are discussing so far about the architecture which are already available. 5G is already available in most of the scenarios. And what if we start thinking about 6G, so new infrastructure, AI native networks, so something which is still not available now, but we are working on to have it available soon. So in particular, I want to stress now on federated learning, because federated learning is one of the key enable technology which enables to have AI native in the network. And one of the most important aspects is security, because security is required specifically inside industrial factories, of course, because in general, companies do not want to share data with anyone in general, of course. So we have the scenario in which we have a set of mobile robots or any other kind of industrial device, which are basically a network of user equipments. And this network of user equipments can communicate, for example, with a remote server or a PLC, or in general, a centralized entity which has the assignment of monitoring all the area, the industrial infrastructure. And with federated learning in specific, in more details, we can have some AI processing and let's say learning within the network itself. So assume that each user equipment, each node in the system, for example, each sensor in the system can collect some data, can process, for example, the vibration or acceleration of the industrial machinery that is monitoring, and then can perform some local training on the local device. Instead of communicating the data to the remote server, it can instead communicate only the model, the deep learning model that it is running on the premises of the local device, so that, for example, the data are kept in a safe manner, and only the model are communicated. Of course, it's much harder to reconstruct the data from the model than having the data as themselves, communicated through the network. And we are interested in, for example, in this project, in industrial network project, in considering what happens is if, for example, some of the sensors in this network are compromised, or, for example, there are faults in the sensor. So basically, if we are monitoring, for example, in this image, we are monitoring an industrial machinery with four devices. What if some of these are not working, and we want to understand how to detect this misbehaving of the system? And in particular, we are thinking of working with graph neural networks in order to monitoring what's happening in a specific machinery. So assume that we are monitoring this, let's assume this robotic arm. And if we have a correlation graph, because in general we have correlation between data collected by a set of sensors on the same industrial machine. So we model this correlation graph, then we communicate some learning metrics, for example, the gradients or the loss of the local training. Assume, for example, we are training the robotic arm to identify which is the metal or the material that is picking, and it has to move from point A to point B. So according to this communication graph, we can model and capture what are the variation between different parts of the sensor, different part of the machinery monitored by different sensors. And I'm mentioning this topic even though it's a work in progress for the moment, in the sense that we are still working on this use case in specific. But I'm also mentioning, again, federated learning now, because security is not the only aspect we are interested in, because, of course, as telecommunication engineer, we also are interested in how to improve metrics into the concept of goal-oriented communication, or in this case, in the context of scheduling and importance-aware scheduling. Because federated learning is, of course, an effective tool to learn in a decentralized manner, but we have to rely on, for example, a high number of communications steps between each node in the system, each sensor, and, for example, the PLC. So maybe we have to to save resources and to organize as much as we can the scheduling. And why not we can use AI for this, for example, no? And we can use this importance-aware scheduling concept where there is an AI model which runs decentralized at each sensor, at each client, and only with some local information, each client can autonomously and locally determine a priority score, for example, to communicate to the server in order to improve the learning metrics in the federated learning system. So basically what I mean is that each client, always enabled by graph neural network, also in this case, I don't have the time to discuss in detail the graph neural network methodology used, but you can have the intuition that through some AI deployed at each sensor, each sensor can understand, according to the importance metrics Basically, according to how much importance my local data have, so I don't need to communicate my data to the centralized server, but it's enough that if I just consider my own data, maybe some data from the neighbor sensors, because we can have some communication capabilities in between sensors, so peer-to-peer communications. And so in the end, each sensor can understand which is the optimal time to be scheduled for each message, not in general. So this is why we refer to goal-oriented communication, because we're interested in the importance not only of the current sensor in the system, but also for the current time step, for the current message, for the current sensor in the system, what is the optimal scheduling policy. So through this decentralized decision, we can see, for example, with this early result that in a system with 16 IoT devices, which are collecting vibrations in order to recognize what is the process metal by the industrial machinery, we can see in the orange curve that through epochs, so basically through the learning process, through the federated learning process, the orange curve shows that if we assign resources according to deterministic scheduling, so basically, for example, a round-robin scheduling, we have a slower learning convergence with respect to a scenario in which we let the client learn and understand which is their importance from their local data, and let them understanding, so what is their priority, let's say, for the current message they want to send. And so we achieve, in this sense, more faster performance in convergence with respect to the learning in the federated learning system. And so the final slide and the message that I want to convey with this presentation is that not only we have to consider industrial networks step by step independently one from the other, we have to consider each block all together. We see that the architecture we decide for the telecommunication network is important, plays a role. The protocols are important, and the AI is pervasive in each part of the overall architecture. So basically, in order to achieve an effective and successful AI-native industrial network, we have to look for goal-oriented communication, and of course, many more interesting and important industrial use cases as the one I hope you like it in the presentation. Thank you.
Thank you again, Lorenzo, and thank you for participating to this session. Thanks to all the speakers. So now the floor is to Roberto for other things, let's say.
We switch to Italian now, since we are going to deal with a totally different topic of...
This is an hijacking of the workshop
level.
by Professor Verdone, and this is a short pitch on the educational offer in our universities in telecommunications, and then we will have the lunch break. Don't forget to vote for your preferred posters. They will be available also in the afternoon, so take some time for going upstairs in the mezzanine and look at the posters.
Allora, abbiamo risparmiato comunque 8 minuti con la sessione.
Bravi.
Così... Il tema è già stato trattato in un'email con una risposta negli ultimi giorni sul reflector di Restart. Allora, innanzitutto oggi mi rivolgo principalmente agli accademici, ovviamente poi quello che fanno gli accademici nel lungo termine si propaga sull'ecosistema industriale nazionale. Abbiamo bisogno di più studenti, lo sappiamo benissimo, lo sappiamo tutti, lo dicono tutti, è venuto a dirlo Marco Rendina l'altro giorno, ieri anche qui, il rappresentante di Astel. Una delle macro obiettivi della mia missione, la missione 5 Education and Training dentro Restart, è questo: mettere in piedi un insieme coordinato, organizzato di iniziative per attrarre più studenti nelle nostre lauree. Ad oggi laureiamo circa 600, ce ne vogliono 5 volte di più studenti, secondo il nostro monitoraggio, in LM27 in Italia all'anno. Allora, c'è un insieme di interventi, quelli che lascio in grigio, di cui parleremo in altre occasioni, e oggi invece questi 5 minuti li spendo a parlare del lancio dai primi di settembre di una campagna di comunicazione nazionale con i fondi Restart abbiamo messo da parte qualche centinaio di migliaia di euro per avviare una campagna di comunicazione nazionale di cui se ne stanno curando in primis gli esperti di comunicazione dell'ufficio comunicazione del Politecnico di Torino con cui collaboro. Allora, vorrei prima dire una cosa. Si parla di denominazione del corso di studio solo dopo che si è discusso quali sono i contenuti dell'offerta formativa. Io, come sapete, ho messo in piedi un gruppo di lavoro di 9 persone, 9 di voi, che da 10 mesi parlano di contenuti e molto presto, mettete in agenda, venerdì 26 luglio, ore 15, vi proporrò un momento, 3 ore online, in cui parlare di contenuti. Però intanto, per motivi connessi alle esigenze dei corsi di studio, anticipiamo il tema della denominazione, anche se dovrebbe venire dopo che si è parlato dei contenuti. Allora, per fare una campagna di comunicazione nazionale, gli esperti di comunicazione e marketing dicono ci vuole un brand, ci vuole una parola, bisogna dire come si chiama la cosa che vuoi vendere. Quindi ci vuole una denominazione comune o almeno una parola chiave comune. Ad oggi l'eterogeneità dilaga su 27 LM27, incidentalmente. Questa è la situazione in Italia, ho rifatto il monitoraggio, è aggiornato a un mese fa. Quindi vedete chiaramente che le parole chiave che utilizziamo nei nostri corsi di studio sono le più differenti. In questo modo non si può certamente fare comunicazione. Ricordiamoci, lo sappiamo tutti, che la denominazione di per sé non attira studenti. Una campagna nazionale forse può contribuire. Quello che conta sono prima di tutto i contenuti, di cui, come dicevo, parleremo a fine luglio. Allora, l'idea è comunque avere una denominazione comune se la condivideremo e a quel punto lanciare dai primi di settembre, come dicevo, una campagna di comunicazione basata su dossier redazionali di Sole 24 Ore, Stampa, Repubblica, digitali e cartacei. Abbiamo già i preventivi di gruppi di influencer social per arrivare al 18enne, che è il nostro target, in maniera diretta ed indiretta. Altre iniziative che passano per le scuole che ora non cito. Qualunque parola chiave, purché sia condivisa, va bene, purché sia condivisa. E quindi siamo qua oggi a cercare di capire se c'è una condivisione. O meglio, siamo qua ad avviare oggi un processo, di fatto l'ho avviato 2 giorni fa con un video, che si vorrebbe concludere nei giorni primi di settembre della riunione GTT a Pisa. Allora, qualunque parola chiave va bene, quindi quale scegliamo? E qui la frase che ha prodotto una replica in broadcast su cui spenderò 60 secondi, un minuto. Allora, telecomunicazioni non è la parola giusta, è la nostra parola. Noi siamo dell'SSD Telecomunicazioni, molto di noi, siamo ingegneri delle telecomunicazioni, eccetera, eccetera. La declaratoria parla di ingegneria delle telecomunicazioni, ma è una parola tossica, quell'aggettivo che ha fatto, diciamo così, scalpore. Allora, il minuto è in questa slide. Per coloro che sono esperti di comunicazione e marketing, è ben noto, cito Paolo Borzacchiello, se volete leggere Il codice del linguaggio, il suo libro che ha scritto 5-6 anni fa, molto famoso, lo scrive sul Sole 24 Ore, eccetera. Per gli esperti di marketing, e noi dobbiamo fare marketing, stiamo parlando di marketing, vogliamo vendere un prodotto, il nostro corso di studio, ai diciottenni. Nel marketing una parola tossica è una parola che non attrae ma respinge. Purtroppo, per motivi connessi a quello che si legge ogni giorno, pensate agli amministratori delegati delle nostre aziende che dicono continuamente che c'è una grave crisi finanziaria, che il governo deve sostenerli, eccetera, eccetera. Questi messaggi arrivano alle famiglie, arrivano ai ragazzi indirettamente e producono tossicità. Ripeto, è semplicemente un termine tecnico, figuriamoci se c'è una considerazione sulla parola che mi porto come da 30 anni nella mia professione e che difendo davanti a tutti. Stiamo parlando di marketing e basta. Ora, quale deve essere questa parola? La parola non deve essere divisiva, quindi non ci possiamo inventare chissà che. Ci sono sedi dove i nostri settori sono più vicini all'elettronica, altri dove sono più vicini alle reti, all'informatica, altri più all'automazione, e bisogna rispettarle tutte, quindi non ci possiamo inventare parole troppo caratterizzate. E quindi la proposta che vi faccio oggi, che viene da un lavoro di mesi di ragionamenti da parte di un gruppo di 9 persone, alcune sedute in questa stanza, che lavora coordinato da me nell'ambito del Restart, la proposta che vi faccio è molto semplice, usare questa parola. In sostanza la proposta è quella di ridenominare i corsi di studio, in particolare le LM27, è più difficile farlo sulle L8, le triennali, però ingegneria della comunicazione o ingegneria delle comunicazioni, con la versione in inglese laddove ci siano corsi di studio in inglese, in qualsiasi declinazione, perché la si può chiamare dei sistemi di comunicazione delle reti, della tecnologia, comunicazione e qualche cos'altro, ma se c'è quella parola chiave, la campagna nazionale che Restart sosterrà con centinaia di migliaia di euro, che partirà dai primi di settembre, sarà a beneficio di quei corsi di studio che avranno condiviso quella parola chiave. Ora, non abbiamo oggi tempo per discutere se quella parola ci piace o no. Lo faremo innanzitutto il 26 luglio alle 15 su Teams. Io vi racconterò tutte le altre cose che stiamo facendo e poi alle 16 riguardo l'education and training, anche, ripeto, interventi verso ministeri e cose del genere, cosucce così, o almeno quelli che vorremmo fare e tentare, e alle 16 avvieremo la discussione su questa proposta che vi sto facendo adesso e anche sulla proposta di contenuti, il cosiddetto Book of Knowledge. Da metà settembre la campagna di comunicazione prende avvio ed è bene che quindi questo percorso si chiuda ai primi di settembre. Parlavo prima con Riccardo Leonardi dell'ipotesi in maniera come satellite all'organizzazione della riunione del GTT, poi sono molto coinvolti ovviamente anche i colleghi SIEM con cui c'è un'interlocuzione continua, insomma l'idea è chiudere lì il discorso. Nel frattempo sarebbe molto utile se voi mi forniste un'impressione a pelle, mi piace, non mi piace, soprattutto la domanda che vi faccio è, per favore andate col vostro smartphone a leggere il QR code, sareste disponibili, capita la motivazione, a tornare nel vostro Ateneo e in consiglio di corso di studio suggerire, proporre, sostenere l'idea di questa denominazione comune, questa che vi ho proposto? Allora il QR code punta a un Google Form dove trovate semplicemente un sì sarei disponibile, no non sarei disponibile e poi c'è un campo libero dove potete scrivere quello che volete. In preparazione della riunione del 26 luglio, ovviamente tutti i commenti che ricevessi nei prossimi minuti, ore e giorni saranno utilissimi, li condividerò con i due presidenti di GTT e SIEM, ovviamente con Nicola, il presidente della fondazione di Restart, in modo da mettere tutto insieme e vedere se arriviamo a luglio con effettivamente, come dire, un afflato comune da poi suggellare con una riunione un poco più formale ai primi di settembre a Pisa. Vi ringrazio per l'attenzione e soprattutto per qualunque cosa scriverete, positiva o negativa, attraverso il QR code. Buon pranzo a tutti.